First, welcome you all to the Khronos Vision Workshop. This workshop is going to be primarily focused on neural networks using OpenVX. Sorry for that. And we have NNEF too. We're going to be looking at Khronos standards, mainly geared towards computer vision and neural networks part. So it's going to start with Frank Brill. He's the chair of OpenVX working group. He's going to just go over the general Khronos ecosystem, what kind of standards we have, and followed that by Peter McGinnis. He is the chair of NNEF, Neural Network Exchange format. He's going to generally give an overview. After that, we have Nicholas and Michael Pennis. They're going to give an overview of OpenVX, high-level overview. They're going to go mention about the whole broad spectrum of what we have in the OpenVX. Then we're going to have a brief, it's not brief, half an hour morning break. So you get a chance to network with other people. You can speak to the speakers. What else? We have a couple of snacks back there. In the later part of the morning, I'm going to present about neural network inference using NNEF and OpenVX, taking something like a TensorFlow model, going all the way to NNEF and then OpenVX. And I have just our guys are setting up. I'll try to log in and see how it works. And after that, Frank Brill is going to come back. He's going to talk about safety critical APIs, primarily start looking from OpenVX perspective. And then we're going to talk about OpenVX extensions. It means things outside our core spec. That's going to be the morning session. In the afternoon session, this is pretty interesting. We have 90 minutes, and we have various vendors. They're going to come and talk about their implementations, how they used our Khronos standards, especially the OpenVX and NNEF. And that's going to be a very interesting presentation. We have a lot of people signed up. So once they present at the end, we're going to have Q&A. And that's going to be the immediately after the lunch. After that afternoon break, we're going to have Andrew Richard. He's going to talk from the SYCL perspective. We have another standard. He's going to talk from how the TensorFlow got accelerated using SYCL, and he's going to go over some from a language perspective on the SYCL later. And then after that, we're going to wrap up with Frank Brill talking from the roadmap perspective, and we have Q&A where all the speakers will come forward and you can shoot the questions to them. Okay, so with that, let's see. Okay, we're just at 9, so I'd like to invite Frank Brill to the podium.
All right, so Khronos is a consortium, an industry consortium with many companies that are joined and participating in it, and Khronos creates open standards that sort of the graphic there in the center, the idea is that we're connecting software to silicon. So there you have silicon that may be very special purpose that does things in graphics or vision that maybe is different to program than sort of your usual hardware. And so the idea here is to provide a standard API that can actually access different kinds of silicon underneath from different vendors, but you can still write code in a portable way. And so the APIs that are provided are royalty-free so that you don't have to pay Khronos anything. All of the funding of Khronos is actually done by the member companies who contribute and participate in that. And so if you get one of these APIs, it's actually, it's been conformance tested. So if you go to your vendor that has the silicon and they say that they support a given API, that means that they have run some conformance tests that were developed by Khronos and actually shown that they're behaving in the right way and getting the right answer. And so you're going to see some consistency across different vendors for the API. And that will allow you to get the performance out of that specific silicon that you don't have to write specific hardware instructions for that particular silicon. You can operate at a more abstract level. And they're very successful, and it says billions of people are using these Khronos APIs every day on their devices. So this is a big shot of the several of them, most of the Khronos APIs that you see that are available now. On the far left, we have OpenVX and NNEF, which we'll talk about in depth today. On the top, there are Web 3D graphics APIs and file formats. On the bottom, there are APIs and languages for parallel computation. And then on the far right, you have the APIs for computer graphics. And so many of you are probably familiar with the OpenGL is sort of ubiquitous on a lot of devices, and Vulkan is sort of the latest and greatest version of the graphics APIs. Of course, we'll be focusing on the NNEF and OpenVX, and also there's a session on SYCL, which is a language for writing parallel computation that takes advantage of modern C++. One thing I wanted to point out here is sort of the difference between APIs and file formats, because we're going to be talking about both today. So most of the Khronos standards are APIs, and that you write a program, usually in C or C++. You call the API and something happens. There's also a set of file formats, and the idea there is that there's a file format that you load, and instead of having a API that you call, you just load the file format, and you can expect a certain well-formed file format. So rather than having a conformance test like you have with the APIs, what you have with the file formats is a format checker, and usually a parser that says, this is how I can read and write these files. So it's slightly different. And you see of course, we're going to talk about OpenVX and NNEF mostly today, and SYCL today. And the arrows here indicate that there is currently an interface between Vulkan and Spear. Let me talk a little bit about the file formats. GLTF is a 3D graphics file format that you can use to describe 3D objects. NNEF we'll talk about quite a bit later today, where you use that to describe your neural networks. Spear is an intermediate language that can be a compiler target, so that what you can use, and if you're familiar with LLVM, it's kind of similar to that, where you compile your code down to Spear, and then the back end can take Spear to your specific hardware. And the arrows there indicate that there is an actual compiler today, front-end compiler from Vulkan and from SYCL to Spear, and you'll hear some more about that later. And then there's the back-end. The OpenVX one is dotted because it's something we talk about, something we'd like to get feedback about, but there's currently not a OpenVX front-end to Spear. So OpenVX, a little bit more about this, and I'll try to stay at a high level so that you get more time in depth later. But basically, you think there's a sort of an inverse relationship between the amount of flexibility you have and the amount of power efficiency that you have. And so as you get up this arrow from fully flexible CPUs up to dedicated hardware that are maybe much more efficient but not as flexible. And what we try and do with OpenVX is actually span this entire thing so that you can actually write code for any of these hardware or a mix of this kind of hardware and have that get used in an efficient way. And what we're looking for here is not just portability as in functions on these other things, but we're looking for something that actually is performance portable, which means that not only will it function, but you will get good performance, something that's approaching sort of peak optimal performance on that particular hardware if you write in OpenVX code. And one of the main things we use to do that is this idea of a graph, which I'm not going to get into too much, you'll hear about it later, but basically the idea of writing your program as a graph that is then compiled to this particular piece of hardware that you're trying to run it on enables this performance portability. So OpenVX has been around for a few years now. The first version came out in 2014, gave us some initial functionality with about, the initial functionality being this graph and all of the API for manipulating it and whatnot. And then particular within the graph, there's particular function nodes that do particular things. And we had about 40 of them to start with in 1.0. And there are actually 24 compliant products, people who have actually submitted their product to Khronos with the results of their conformance test and shown that they're actually functioning properly. And those 24 products are from 8 different companies. 1.1 came out a couple of years later. We added some more functionality and both tweaking some of the stuff about the way we use the graph and adding a few nodes. And so that's the sort of most implementations that you would get today would be 1.1. And so and there's 18 compliant products there. And then finally, 1.2, which was released actually at the Embedded Vision Alliance this last year. And so it actually added quite a bit of new functionality for conditional nodes so that you can do things like, instead of always executing the entire graph, you can, based on some early results, you can partially execute some of the graph and not of the other graph. And then there's more nodes for feature detection and classification and imaging. So they added quite a bit of nodes. I think we're up to 63 nodes, something like that. And we also added some extensions for neural networks, which we'll talk about some today. Graph, save, and restore, also, which we'll talk about some today because it's important for the safety critical there below. And 16-bit operation. The safety critical is a version of the spec that's based really on the 1.1. Basically, the 1.2 development and 1.1 kind of went on in parallel. I'll talk more about the safety critical, but there's a version of the spec based on 1.1 that came out also last year. And what we've been doing in the last, since then, really is working on extensions. And the 3 extensions main mentions here, pipelining, streaming. It actually gives you, if you're running a series of images, it gives you more efficiency and optimizations that you can do if you're streaming a bunch of images through your graph. There's an interoperation between OpenCL so that you can do some of these nodes in OpenCL if you want to add your own functionality and have an OpenCL capable target. And then NNEF. And there's a way to import a kernel, which could be NNEF, it could be something else, but one of the main drivers was to be able to import an NNEF graph. And we'll talk about that more later. The roadmap, there's a session at the end of the day where we'll talk more about the roadmap, but we've got a lot of things that we're thinking about and working on. Some of them are progressed more than others, but we want to get your feedback on your being all the community and people who are interested on what we should add. So OpenCL is a low-level parallel programming language that you have complete control over exactly what happens where, which is great if that's what you want. And if you want to be able to, well, there's an interface between OpenVX and OpenCL so that you could have a node that is actually implemented in OpenCL, and you have all of this capability to control everything and get good performance there. And so there's sort of a layered ecosystem. Actually, and Neil has a slide, if you look at the entire, not just Khronos, but the entire sort of community, that there's more layers here. But just here, an idea is you have your application, you write an OpenVX. That OpenVX application could be implemented, the actual OpenVX functions could be implemented in OpenCL, or they could be implemented in C++, just depending on the target you're on, or even on dedicated vision hardware. And to you, that's sort of transparent. There's a lot of information on this slide, but just briefly how you compare these different alternatives. OpenVX, we'll talk about obviously today, and OpenCL I just talked about. Those are 2 Khronos standards. You're probably familiar with OpenCV, which is an open source library with lots of computer vision functions in it. The difference, of course, between that and the Khronos ones is you can get a, say, conformance test. There's a specific spec that says you must do these functions and you must get these results for both OpenVX and OpenCL. So we have this governance and conformance model that enables you to see, you know what you're going to get. Whereas with OpenCV, it's this huge library, and especially if you're on an embedded target, typically what you're going to get is whatever the the vendor implemented and decided to port based on their hardware and what their targets are. So there's no sort of really consistency, especially in terms of embedded hardware, for what functions you're going to get with OpenCV. With OpenVX, you do get that consistency based on the conformance test. Finally, a word about safety-critical APIs. So I mentioned that, Khronos has experience with safety-critical coming from the OpenGL world. And so typically what you do with, or what we have done, what Khronos has done with safety-critical APIs is you take the APIs that have been defined without really necessarily even thinking about safety critical, and you look at those things that might be unsafe and you take them out. So things where you're doing a lot of memory allocations or you're chasing pointers around and things like that, you just take out that bit, or maybe you'll modify it to make it a little bit safer. And so that was done for OpenGL. But really, we need to do more, we think, based on what's happening in the community and the fact that, especially when we're talking about, say, vision, and that might be driving the car, we need to do more to enable those safety-critical APIs and those safety-critical implementations of the APIs. And so what we've done with OpenVX, I'll talk again more about this later, is that we have a safety-critical version of the OpenVX spec. And there's a number of things that we did where we cleaned up, as I said, things that might be unsafe. We made some changes, and there's, I don't want to, again, there's a section about it later, but we restructured the API to make it so that you can deploy in safety-critical environments. But exactly what to do for safety-critical in a broad sense, especially at the API definition spec level, it's not. It's a work in progress as to what to do. So there's something that Khronos has put together called the Safety Critical Advisory Forum, where we can get feedback from the community. So you're welcome to join that, and we definitely would appreciate the feedback from the community there. So that's the last one. I just gave kind of a rush through an overview of the things that you'll see. Many of the things that I talked about we'll see in more depth here as we go through the day.
Morning, everybody. I'm Peter McGuinness. I'm the chair of the NNEF working group. That's Neural Network Exchange Format. And I'm going to talk to you mostly about that, a little bit about how it relates to the OpenVX standard, and a little bit about the ecosystem and how it relates to other exchange format standards, the other exchange format standard that's out there in the market. It's an informative session, so feel free to ask questions. Don't bother about stopping me. I'll answer questions live. And I'll try not to get too far off track if you do that, but it's fine. So if you do have any, we actually have a room mic, which is over there with the lady who is running the AV. So it's easier for other people to hear what you're saying if you grab the mic, if that's convenient. Okay, so let's get going. These are some general slides. Frank's introduced Khronos. This is a kind of a restatement of the Khronos mission, so I'll skip over these fairly quickly. But the list of companies that you see there in the panel just gives you an idea of the scope of the participation in the standard setting process that we've got at Khronos. And that's one of the major strengths, is that we get buy-in from not necessarily all the companies who are in this list, but they're all available and they all have the opportunity to contribute, and many of them do. And many of the most prominent companies in that list have contributed both to OpenVX and to NNEF. And then Frank pointed out how many billions of units are shipped with Khronos APIs. Mostly OpenGLES, I have to say, is the standard. This is a restatement of the principles of organization. Anyone can join, anyone can take part at various levels of participation, up to, with paid more money, the governance of the organization itself, which allows you to influence the trajectory of standards and which standards we actually consider for implementation. All right, so why AI and vision need standards? The simple statement is that we're trying to enable an industry which can accelerate these functions. We started off with graphics and moving into AI and vision. The whole idea is to reduce the fragmentation of the platform, and this is key, a key idea behind the NNEF concept. Because without standards, you get fragmentation. With standards, we can provide, a standard provides a consistent deployment platform for whatever technology it is that you want to deploy as application vendors. So on the hardware vendor side, you've got a mechanism to make your platform more attractive to software developers, and on the software developer side, it's really critical in an industry, any embedded industry, that you have a platform which is consistent across all the many varied types of hardware that are out there. And so you have the proprietary platforms like Android has its NN API now for deploying neural networks. Microsoft have their gosh, I forgot what it's called, DirectML, I think. Apple has the equivalent, et cetera, et cetera. Those unify the platforms, but we also need a way to transfer the networks into those deployed platforms. So that's what NNEF is all about. It's all about making it possible or making it appear that there's a single consistent platform that application developers can target for their application, their software development. So with NNEF and OpenVX, the way that they kind of relate is that we've got a diagram here of kind of the flow of a deployed application. You have a vision application, which can be running on whatever device you're talking about. The application interacts with the vision sensors, and it imports the trained networks, and OpenVX provides the infrastructure to run to accelerate the application functions that you want to create. So these things play together in order to provide a seamless end-to-end deployment path for your application. And we're going to see that a little bit later on, because Rada from AMD has come along with an actual implementation of that flow from ingesting a network using the NNEF format and then running that inference on an engine which is running OpenVX. Okay, so this is the workflow of neural networks. On the one hand, you have frameworks, and you've got many frameworks, and you have desktop and cloud hardware, which generally run training and inference engines, which are sometimes accelerated in special purpose hardware, sometimes just run on lots and lots of CPUs. But the point here is that the neural net training frameworks are many and varied. I think eventually they'll settle down to fewer, but right now it's kind of a Wild West situation. So from Google, you have TensorFlow, very famous. That's by far and away the largest and the most pervasive training network. But you also have CNTK from Microsoft. You have PyTorch, Caffe and Caffe 2, which are being promoted by Caffe 2, being promoted by Facebook, and there are others as well out there like Chainer and network training frameworks like that. They all have their own internal formats, and they all have their own proprietary export formats. So you have this variety of training frameworks, and one of the things about the frameworks is that they've each been designed for a specific to enhance certain specific capabilities in the network training. And so there exists a need to move between training frameworks depending on what you're doing. You might be wanting to use a more researchy type of framework at the early stages of your work. You might want a framework with more precise definition capabilities when you're moving towards implementation. And so you might want to move between the frameworks. Now that becomes a problem if the framework formats are different. So one of the objectives of NNEF is to allow the transfer of trained or untrained networks between training frameworks. And that's illustrated up here. This is this sort of feedback path that we've got going on here. It also mentions the ONNX, which is the Facebook promoted transfer standard, which is kind of a competitor to NNEF, although there are some differences and there are some strengths and weaknesses of each, which make them more or less appropriate for certain applications and certain uses. And I'll get into a little bit of that later on. So that's the first objective of NNEF. Now on the other side, this is at the embedded inferencing side. You've got a wildly varying scenario where you've got different inference engines deployed on very different platforms with extreme differences in capability, and they're running, in general, proprietary accelerated hardware, and you need to get your neural network into that environment with as little fuss as possible. So this is the other application where NNEF comes in. It's the other part of the flow. You have this enormous variety of trained networks, and in the worst situation, in fact, the situation that we're in now, which is this, we have a many-to-many mapping. If you're working in TensorFlow and you're going towards someone's deployment platform, you need a converter explicitly from TensorFlow to that platform. If you switch platforms, you need a different converter. If you switch training frameworks, again, you need a different converter. So you've got all of this confusion, this straight line spaghetti, I guess, in the middle of the diagram there. So the purpose of NNEF is to ease that problem. It's to make it so that you really just don't have to think about transferring between training and inference. So the bottom diagram there shows the situation that with export modules for each of the training frameworks, you just export to NNEF. The hardware, the accelerated hardware vendors provide a single importer from NNEF to their inference engines, and you're done. It's something that it just removes one complication step from the process. A good way to think about it is the way is the purpose that the PDF format serves in publishing. It's a universal format that everyone can read, and it produces more or less the same results. The results are implementation dependent, but the transfer format is consistent. It stays the same, and you know that if you observe that format, then when you're outputting in PDF case, a document, in the NNEF case, your network, you know that any compliant hardware which is out there will be able to execute. At least it'll be able to understand your network. Whether it can execute it or not, whether it can run it and produce the right results, that's the job of the hardware vendor, to make sure that you can do that. But the format is fixed, and it takes that step out of the process. Okay, so we have a lot of different deployment paths. We've picked up a few here which are deploying on sort of standard platforms. So these are illustrating platforms that are available on specific operating systems. Starting from Onyx here, we've got the flow shown through the stack, through the Microsoft stack, down to DirectML. That's their low-level kind of equivalent of OpenVX in their world. And that's one route. There's the TensorFlow route through to, it could be any framework actually, but we've shown TensorFlow going through to the Android neural network API, NN API, and then we've got the Apple Core ML example. And this is just to show you that even across fairly high deployed platforms, there are a lot of different interfaces to work to. They're kind of converging, but they've got their detailed differences. Now, the intention on the NNEF side is to handle all of these deployment platforms. I'll talk about the developing ecosystem in a minute, but the intention is that you would be able to take an NNEF network and deploy it on any of these OS platforms. Now, extra to the OS platforms, you have the embedded systems, which may not be running a sophisticated OS like this, which they need some deployment path. And that's where something like OpenVX comes in, because that can be deployed onto an embedded, say a platform that's running Linux, which doesn't have any of the infrastructure which is provided by all of these examples here have their own inference engine, right? So you go down to their low-level infrastructure. Without that infrastructure is provided by OpenVX. So it's important that we have deployment path through these these routes, and also through the embedded routes. And of course, we work most closely with OpenVX. You can have your own custom implementation of an inference engine, but with OpenVX, you really don't need it. Okay, so this is kind of how NNEF fits into its ecosystem. So a brief word about what NNEF is and what it looks like. So it's a file format, but it's actually it's more than one file format. It's kind of a multi-file format. It has a directory structure associated with it, and so we have formal definitions of the syntax that describes the network in terms of the shapes of its tensors, the operations that are performed, and then you can add certain information to those descriptions to specify or to give hints to the inference engine as to how this network was trained. So there's certain operations that can be defined as quantized, and you can define what the quantization method is that you need to observe in order to produce the same results as the network was trained to produce. So that's a file which describes the structure of the network. And then there's a separate file, which is binary format, which describes the trend weights of the network. And so when you run your inference, you combine those two pieces of information. You ingest the structure description, parse it, and produce the actual network structure. And then you apply from the binary file, you apply the weights that turn it into an actual trained network. And when you transmit the NNEF information, it can be transmitted with or without training data. So you can just transmit the structure if you like, and then train it later. You can transmit the structure with the trained weights, and you can transmit it with multiple sets of trained weights. So you can have a single structure, and you can have multiple binary files describing the training results from various training structure. So depending on the hardware that you're deploying on, you might want to have one version which just runs in 32-bit floating point. Another implementation, which is much more likely in the embedded world, you might want to be able to transmit the weights which are specified for, let's say, quantized down to 8 bits everywhere, and you can do that. Or you can transmit a file that's been trained with some of the weights have been quantized, and others are in floating point, or you can have in different fixed width training. And all of this is described inside the structure of the file. The structure of a network it's a series of nodes on a directed graph, and you have nodes which are which describe the shape of your tensors, and you have nodes which describe the operations that are performed on those tensors to produce the results. The tensors, of course, have fixed shapes. The operations are described as hardware-independent, kind of infinite math operations. So we don't say you have to run this in 32 bits, a multiply or a multiply accumulate. We don't specify any data format there. We just say it's a multiplication. And then we supply a hint, which can tell you that actually we trained this and we used 8 bits at this stage, at this node. Or if we don't tell you what that format is, just assume it's 32 bits. And then you go ahead and you can run a tool to optimize the network. And at that point, you will apply some quantization. So all of this information is carried forward in the structure of the structural description of the network. Okay, so what you can do with all of that, at the moment, we have exporters from TensorFlow and Caffe, which have been supplied by one of the members of the working group. It's AI Motive is the company that's supplied that. They've supplied those exporters along with a parser, which is available. All of these things are available as open source on GitHub. So you want to pick these things up, you go along, pick them up from GitHub. If you're writing an inference engine and it wants to import NNEF, there's a parser there already which will parse it for you. Just pull that in, put that there as the front end of your software, whether you're building a tool or whether you're building sort of an inline deployment engine, and you should be good to go, right? And the parser itself is maintained as a Khronos project, and we have a Logo program where it's not compliance. It's not compliance in the sense that you have to pass compliance tests that in the same way you would for an API, but it's conformance in the sense that you if you can run the parser, and the parser says that you've produced an NNEF file with valid NNEF syntax, then you're conformant with the transfer standard. Now, you can describe nonsense in that way, just as you can write a PDF document that contains nothing but gibberish. It's still a valid PDF document. So even a nonsense file in the NNEF format or set of files can be valid syntax. It's still described nonsense. It's up to you to make sure that you describe your network correctly to produce the results that you want to produce. But at least the file format will be conformant with the standard. And like I say, we have a Logo program that allows you to stamp your system to say that we are producing NNEF conformant files using this, whatever your tool is, whatever your product is. Okay, so today we have TensorFlow and Caffe exporters. We have the syntax parser. They're identified in the green boxes on here. And we just announced earlier this week that we have a project ongoing with a company called Ozone, who I think are going to be showing something here today. They were showing on the show floor yesterday and the day before. And for us, they're going to produce two new tools which are importers and exporters for Caffe 2 and for TensorFlow in its native protobuf format. The TensorFlow from AI Motive is the other format. So we'll get coverage, and this is going to happen within about a quarter. We'll have coverage of the two most popular and significant training frameworks in valid, in useful formats. And so you'll be able to exchange between those two networks, and you'll be able to export from those networks into your inference engine, all with open source software, which will be available on GitHub. And once that's released onto GitHub, of course, being open source, you're able to join in, enhance, and make any. You can fork it for yourself and produce your own version of it. Or you can just use the stock exporters, or you can go ahead and build a plugin for TensorFlow and give it to the TensorFlow guys if you want. We'd love that. And we also have a couple of other projects in flight. One very significant one is a project which is being run by a company which is a spin-off of NTHU in Taipei, and they're producing this thing here, the converter and importer into Google's NN API. So that provides a deployment path onto a huge number of mobile phones and other devices on Android 8.1, I think it is. And that's in flight. It's probably about 25 or 30% completed. So that'll be coming online in just a few months. So by Q4 of this year, we'll have all of those elements of the ecosystem in place. And of course, for the embedded industry, the non-Android, non-Windows industry, we've got OpenVX, which is it's in pink. It's actually there and working right now, but it's not actually available as a piece of software for you to use. But it will be in the pretty near-term future. So the discussion of open source brings up a few issues that are relevant in that area. So the purpose of a standard is to be stable. The major difference between what we're doing at Khronos and what Facebook is doing with ONNX is that they've gone open source from the very beginning, even for the definition. It's all open source, it's community generated. Their strength is that their promoted strength is that they can move very quickly, they can upgrade, they can change, they can respond to mistakes and enhancements very, very quickly. The downside of that for the embedded industry is that you can't afford to have your standard deployment platform changing every 6 weeks or less. And we've seen the specification, real material items of the spec of ONNX change 8 times over the past year, which is fantastic for them. You can do that. It's a massive headache for people who are using Cafe or Cafe 2 and wanting to interchange, but they can respond in software. It's very difficult to do that if you've got a piece of hardware or a piece of embedded software which is deployed on however many IoT devices around the world. It's very difficult to keep up with that sort of thing. So the benefit of NNEF is that we have a defined specification. We released the version 1.0 provisional in December last year. We'll be releasing the full version, the final version of that, which contains a few changes and enhancements, but is not significantly different from the provisional version, and we'll be releasing that within a few months, hopefully within 2 months. And so that will be available, it'll be stable, and we won't change that until we come out with the next version, which will be a minimum of a year or so. So then you ask the question, okay, how do we respond to changes? It's a fast-moving industry. How do we actually respond to some hole in the spec? Because we don't know everything today. We've tried to include everything, but we don't know everything that could be included. And tomorrow someone could come out with a network that nobody knew about. And we need to respond to that. Some function. Someone might come up with some, wacky pooling function that we don't cater to. So you need to be able to respond in that way. And the way that we do that is that we have extensions. And we have 3 types of extensions that you can add to the standard. This is so you can take the standard and you can create a private vendor-specific extension and implement whatever function you want, and then for your own private purposes, you can write your software to make use of that function. That works well if you're in a very vertically integrated situation where you're producing a piece of equipment, I don't know what it might be, some camera-based equipment, where all of the software is written and verified and used only by yourself or your customers. That works very well, and you can do that. And you can propose those extensions, and you can make the modifications in the open source software so that, for instance, the parser can understand them. Other people don't have to use them. Then the next way is to have a vendor extension which is identified and registered with Khronos that other people can take advantage of if they want to. And that's kind of the next level. It's the same sort of process. You provide the implementation for the parser. People, with a file format, every function is voluntary at the ingestion end. As long as you can understand the syntax, you don't have to implement everything that is defined there. You just say, my hardware can't do that, and that's fine. But as a vendor, if you want to make that available because your hardware can do that, you have the vendor extension mechanism. And then there's the Khronos extension mechanism, which is, these are proposed and ratified and included as extensions by the working group. And those are extensions which, by their nature, they've been considered by the group. They're seen as essential. They're added to the standard, and the likelihood is that they'll make it into the next version of the standard without any changes. So you can get a preview. So that's the way that we respond to the fast-moving nature of the industry. And you can all participate in that through the open source project, through the GitHub projects, if you want to be able to do that. Okay. There's some detailing. How much? I have a few seconds left. But that's good. I just want to mention the OpenVX path. So OpenVX has added a neural network extension. where you can define neural networks as OpenVX nodes in its kind of a subgraph. And the intention is, well, it's coming along. The NNEF importer will just import a predefined network into that as a single node into that graph. So it kind of so you've got two paths. You can sort of start building up your network inside of OpenVX, or you can just import a fully formed network through NNEF. And going forward, that ability to import a fully formed and execute a fully formed network will become more and more robust in OpenVX as time goes on to ease the process. So you don't really even need to think about it. You just tell your OpenVX graph. You have the whole graph put together from your camera through to whatever the target is. You can just import that NNEF file as a graph, and it will perform that function without pretty much any further thought. And with that, I'll stop and ask for questions.
Does it work? Okay. Yeah, so you mentioned the NNEF node, you can put some hint there, right? So does it mean if you run a NNEF on different hardware platforms, the result not necessarily be matched?
That's correct.
Okay.
So the way that it works is you can define you define nodes, a computation node, with certain function. Say the functions are they're called fragments, and they're at the level of it could be a multiplication, or it could be a ReLU operation, something like that, or a pooling operation. And what you do is at that stage you tell the network, you include in the network what's essentially a hint. So you say that we're going to do this function, and it was trained with let's say 8-bit integers, right? That's in the file. If the file is supplied with data, let's say you're defining some of the weights as being 8 bits or 16 bits or something like that. That will match what's in the binary file with the data. But you're being told at the inference engine level that this operation was performed using 8-bit arithmetic. But you don't have to implement it as 8-bit arithmetic if you don't want to, right? I mean, you're just being told that this was what we did when we trained the network, when we got that result. So you can run it at full floating point if you like. You don't have to do. It's likely to go in the other direction if somebody telling you that we trained this network using 16-bit half precision floats, but you've only got 8 bits, right? That information is transmitted into your, let's say it's an ingestion tool now, rather than just a straight flow through to the inference. You can suck it into your tool. You can look at it and say, well, it was trained using 16 bits. I don't have those available, or I can do better than that. And then you make the appropriate decision for your hardware.
I see.
Yeah.
So then the conformance, so basically it's a syntactic, not a semantic.
Correct. Yes, that's right. So the conformance is to ensure that the whatever the framework is producing valid syntax, right? And as I pointed out earlier, that just like a PDF, you can produce a valid PDF file and it contains nothing but nonsense, right? You can produce a valid NNEF file which contains nothing but nonsense, but it's still a valid file. But that's still a you'll still be able to read that nonsense, and that's the point.
Okay, thank you.
May I just add to your last comment?
Sure.
I think in terms of that analogy to a PDF, I think if he may be saying it's not just about putting gibberish in the PDF file, but it's like I am rendering a PDF file and different people may be rendering the fonts differently, or they may be showing it differently. I think that's his point as opposed to what's contained. It may still be whatever gibberish, but everybody else is supposed to display it the same way, but not in this case. And I'm not. It's not a comment about
that's
NNEF.
a very good.
Yeah.
It's a very good point.
Exactly.
You're
So that's the
completely
key
correct.
difference,
Yes.
yeah. Okay.
Yes. Okay, we got another question.
Are we allowed to concatenate networks? Because I have one network with one structure, one set of weights, and I have another sub-network with another set. I want to put them together, create a new network, and retrain a little bit. Should that be allowed with these files?
Well, I guess you could put two networks in one description. There's nothing stopping you. The shape of the network can be anything you like. But do you mean, can you do it automatically? Or?
I mean, does it have provision to append network, like, I append two files and get a bigger network? Those headers and footers and all that?
Well, you would have to. So basically, the structure file format is just a text file, right? But I mean, there's no append function. So you would, if you wanted to do that, you would create a new network, right? Yep.
A question about fixed point representation, not necessarily integer, but with fixed point there's value and the exponent used. How the file formats support this additional, or the binary format supports the additional storage of the exponent for the weights, for example. If that's a better question for offline discussion, we can take it.
Okay, I'm not quite sure what the.
I think he's asking for proprietary floating point as opposed to fixed integer.
Well, sure. I mean, if you have a proprietary format, then obviously you need to know if you supplied those weights. Then you need to know about that in your. Actually, you can answer that. Rada's got a better handle on that.
Sorry. So we do have a room for extending. So let's say if you have, let's say, bfloat 16, let's say something like that, what Google is using, you can extend your format. We have a placeholder for that.
Okay.
Yeah, yeah. And then if you find something really useful, you can bring it to the Khronos, and we'll try to locate to that. We can standardize as an extension. If every vendor says, yep, that's the way to go, we'll standardize that.
So hello everyone. So I'm Niklas, and now we're going to dive into some OpenVX details. So like you already mentioned before, also for OpenVX, one of the main motivations is that we want to have a portable API over all platforms, but we want to be able to enable fast, efficient execution with the best acceleration available on each platform. And then there is a recent addition, then obviously with neural network support, which is sort of the current hype. So I have an illustration here. It's a sort of overview graph to show what you will be able to do. I'm not going to go into detail quite yet, but it's a mix of OpenVX nodes and a CNN, and you can connect them and have interoperation between them and have a quite complex algorithm. This example is with some kind of input from a camera, and then you get some output a result that you can further analyze in your application. And so about API portability. Every vendor supporting the OpenVX, they will implement their own version of the standard. I mean, not version, but their own implementation of how to execute under the hood the APIs. And it's then tailored to be optimally efficient for each platform, but then hardware independent. And hardware independent means code portability, like I just mentioned. And this basically means the same. You write the code once, and it will run everywhere, without. And I put in a little m there, without many changes, because in the ideal world there is not even a single line change, and it just runs. But you have the option to do minor things, like for instance, give a hint as to which. If you know there on certain platforms you will have the availability to run on a certain type of acceleration, then you might have already on that level a design of your application that's slightly different, and you can give a hint that if available, run like this, otherwise run like that. So there's minor things like that, but it's still fairly, I mean, it's to get the best out of both worlds, I would say. So it's very, very portable still. And for as goes for the standard, there are 3 parts of the standard, and what we usually talk about most is the API specification, and that's where you specify how you interact with the standard, which kind of calls you can make, and what kind of result you expect to get back. And then we have another part, which is the sample implementation. And it acts as a kind of a guideline for how you could implement it and the example of an implementation. And it's not supposed to be a reference as such, so you can't test against it. There might be, I mean, we're not really guaranteeing that every operation is exact, but we're trying to do as close as possible to help vendors to understand how they could implement it. But there's also one other side to it, that as a developer, you can also run it on the PC and test your algorithms to see that you get the kind of output that you want. If you're processing an image and you make a sanity check that it's going to run slow, but it's going to produce the right result. So before you put it on the actual hardware, you know it's going to do the right thing. And then the third part is the conformance tests, and that's mainly mainly for the vendor who is implementing how to execute it under the hood, then to be able to show that to the buyer of the product or whatever that okay, this one is compliant, so you can expect that it will do what the standard says. And now leaving over to Michael.
Hi. Well, yeah. Can you hear me? It's all good. Yeah. So Frank mentioned this, that the concept how we actually write our algorithms when we use OpenVX, it's a graph concept. So you probably know this from if you know TensorFlow, or if you even attended the workshop on Monday, or it's a concept of a computational graph, right? So this is the basis, the fundamental concept of how you actually express your algorithms in OpenVX. So it's just an illustration of a real simple graph, and it's a DAG, we call it, and it's not the type of DAG that Brad Pitt would talk about in Snatch, if you know that reference. It's a directed acyclic graph, right? So directed, we have data flowing through the graphs, and the nodes are function calls, or the computations that you want to perform on the data. So you have images, it's a very common case. You want to perform some processing on that, right? So the data flows down, so you need to have it directed. You need to know what's the input and what's the output. Otherwise, results will be very weird, I think. Acyclic, so we don't have any loops in there, right? So it's the acyclic part, and yeah. So this is a good concept. And the nodes are the computational kernels. So the nodes are the actual functions that you want to perform on your data. Let's see. So as an algorithm developer, I mean, we want to express our algorithms in, maybe we have written them, some just as a functional description. Yeah. As sort of imperative programming, you just need to express them as a graph, and that can be troublesome sometimes. You know, you can't have the loops, for instance. You can't have a bunch of if statements and stuff like that. But this can be good because no more spaghetti algorithms. So OpenVX unboils your spaghetti, right? You have this sort of more. You need to formalize your algorithms, and the place you want to use OpenVX is usually in the very pixel-intensive algorithms, right? You need to optimize those. And it's usually a good thing that those are pretty deterministic in runtime, for instance, so you want to have them. They're usually expressible in the graph format. So this is a nice thing, could be a troubling thing a bit for algorithm developers, but for hardware, I don't know if we have any hardware developers here. We're looking, yeah, so a couple of guys. So I think you probably like this concept even more, right, of having a graph, so you don't want to have a bunch of branching and stuff like that. So that's the concept of getting this portable efficiency. So that's the key enabler of that. So there are some optimizations that hardware vendors can do, a couple of different layers. Rada mentioned this in his talk on Tuesday as well. I don't know if you saw that. So you can do graph scheduling, right? We've heard that we can have multiple types of hardware running OpenVX. So the whole platform will abstract that away. And you can run some nodes that are efficient to run on this GPU thing and something else in this very dedicated vision hardware. And the OpenVX framework will take care of that and schedule those different function calls to different parts of your hardware. And we can also parallelize computations. I don't know if you saw in the previous slide. It was just a simple example. You take a YUV image, you do some extractions. But at the very end, you have these two, the magnitude and phase node. You take a gradient image and you compute the magnitude and phase. Those two operations can be computed in parallel because they're not reliant on the same, after each other. So that can be parallelized by the OpenVX runtime. Memory management. This is as I find, this is often a place where you can do a lot of optimization. So you can do a lot of mistakes, right? So memory copies is usually very, it can be very slow. And the concept of having a graph like this is that intermediate results, one thing, they can be optimized away because the user, you don't need to access that data. You need to input your input data and get your output. But everything that's in between, an OpenVX implementation can decide to optimize away or make more efficient. And yeah, we can have memory at different places. I mean, not everything is in RAM. Something is dedicated hardware memory. We have a concept of kernel merge, which is sort of express a couple of function nodes in OpenVX, but the hardware might have a combined operation for those, so a very efficient instruction. It can merge those kernels, and so then we don't need this intermediate image at all, and it will be optimized away. You don't need to care about this as a user of OpenVX because it will happen by the implementation. So that's the portal part. They can also do data tiling if to get better cache utilization depending on the implementation. Also something you don't need to care about as a user of OpenVX, so that's something that happens under the hood, and these are a couple of points that are, I think, liked by the hardware developers. Got some nods from you guys. So let's see. So a quick example, Rada has done a tutorial, I think. It's on GitHub, right? If you GitHub OpenVX tutorial, you will probably find an example like this. Something you can just prototype up real quick, just to get a sort of quick feel what you can do with OpenVX. And if you're familiar with OpenCV, you will probably recognize some of this stuff. So we have some camera input. You want to input that into the OpenVX graph, right? So you want to do some algorithm here. You want to have portable and fast, efficient. So we input an RGB frame. We add a couple of OpenVX nodes. Simple color conversion, channel extracting, yeah. So we get the gray frame out of this. And these two can be, this is a pretty good example of something that could be kernel merged, right? Because an implementation might take an RGB and directly output the Y component. You don't need other parts. Yeah, so we create an image pyramid of this. Get some pyramid images. Detect some corners using the Harris corner detection algorithm, which is one single node in OpenVX. You get some points here, some key points. And we track these. You can use Lucas Canad, optical flow tracker. I don't know if you saw the keynote by Canad. It was really good. But that's another node, right, in OpenVX, the optical flow tracking. So it's pretty simple from an algorithm developer. Just, yeah, OK, I want optical flow. I'll add a node, right? And it will be optimized by the hardware if it's possible. And then we track the key points and we get some output. So it's a simple example, but yeah, I think it's simple, right? Rather the code is online, so it's very simple like that. So what type of functions do we have here? These nodes, what type of nodes do we have in the core specification? There are a bunch of them, 63 we said, right? We have some element-wise functions, simple ones, add, subtract, even do a lookup table, and these image processing types. We have filtering functions, a bunch of filtering functions, commonly used in traditional computer vision. We have some geometric functions. You need to rescale your images and stuff like that. We have some reduction functions. Not everything, it's not only images, right? So we can get some mean values, some standard deviations, things like this. And then we have these complex functions. We have an entire tracker within a single node, and a corner detector. We have some control flows, Frank mentioned before, so we can parboil our spaghetti algorithms a little bit. We can have a select statement, which is sort of like a switch, the conditional execution. Like some part of your graph you might not want to execute depending on some value previously computed. So you can have some data dependency within the graph. So yeah, it's a bunch of examples, and the specification is, of course, online. So if you're not satisfied with these ones, you can add your own. So it's a concept called user kernels. You can get your custom algorithms right into the OpenVX runtime. So a vendor extension, for instance, as we've heard before, has some super optimized, a new type of operation that you want to be able to use that performance in your applications, and you also get this sort of the scheduling advantages and all this kind of stuff. And if you write your own algorithm, as opposed to you have something that from your hardware vendor that's optimized, you have your own special algorithm that you really want to use. can run it either on CPU, it can be pretty slow, or you can use the OpenCL extension to get some better performance portably. And we will see examples of this OpenCL interoperation extension later. More details. Yeah. So this is just, don't want to spend too much time looking at this code. It's online, but it's a C API, right? The specification is in C. So this is basically how it looks like. We call a function and we get a node back. So we get an object, which is a VX node. In this case, it's a thresholding operation. We put it on a graph. We have some inputs, an input image, an input threshold object, and you get an output. So yeah, really a simple example of how it looks like. So some code here. Don't want to spend too much looking at the code, but just to get the flow of how you actually use the API, right? There are tutorials online, but so you create a context. The first thing you do is you create a VX context, because everything needs to be in this runtime environment to enable the implementation to later make all these optimizations. You create a context, you create some data objects, input and an output image. Yeah, these are obviously important for you as an application developer. You need to know this. Then you create a graph, right? So here you start building your functions inside the graph object. So create an intermediate image, and these are called virtual data objects in OpenVX. So these are the ones that might be optimized away, and you don't have access to this actual data. So this is just a virtual image. You add the function node, and you connect it together using the images, the input and output. And now the output is just an intermediate. This could be this color conversion node, for instance, in the last example. You create another node, connect it to the output, so we can have the channel extraction. So this graph would then consist of RGB in and a Y out, Y channel. And then we do something important. We do a verify graph. So this will ask the implementation, or tell the implementation to, now I've finished making my graph. Go ahead and compile it, make all these optimizations, and I'm done with the graph, basically. This is the algorithm that I want to run. And the graph is verified. And then hopefully it's verified. If it's not verified, you might get some errors. But so then you want to process this, right? So inside the loop, the verify graph stage, that could take some time, because the implementation needs to sort of might compile it to its special assembler instructions, all this stuff. But then, so inside the loop, it will be really fast. That's the main thing. Here you only update your inputs, process the graph, you get the outputs, update some parameters, etc. So we've seen some of the functions that are in the core specifications. Here are just a list of some components that we need to build our graphs. We saw some of this in the last slide. Everything lives inside a context, and you have data objects. So images and a tensor is an important one. That's in the core specification, and that's obviously important if you want to do neural networks. You're not satisfied with three dimensions of your data. You need a fourth, and other data objects. There are kernels, which are the functions, and these can be the core specification functions. It can be vendor extensions, your own extensions, your own functions. We have the graphs, which are built up using the function nodes, as we saw before, and the virtual data objects. So those live inside the graph. We have some extensions, which we'll talk more about later, so I won't go into them at all. And there are some other parts of the framework. For instance, you can do some performance measurements, logging. You can have these hints, as mentioned before, where to run, where you think that your part of the algorithm should be run. The memory management. So one key to actually getting this performance out of them is enabled by the opaque data access. So you don't have direct access to the pixels, for instance, when you create an image. So this enables the implementation can allocate the memory wherever it sees fits, right? So where it's mostly efficient. So you can't just directly grab a pixel. So you need to map and unmap it. So if you create something, you create maybe a lookup table that you want to use for controlling your graph. You create the type, and then the open frameworks, the implementation, I guess the runtime, owns the memory here. So then you want to update it, you map it to your application, and then when you're done updating your table, you unmap it, and then it's owned by the OpenVX again. Yeah, and then you can release it, of course. So how do we create images into here? We saw it on a pretty abstract level. Just a point, how is this arrow actually done? As we saw before, you can create an image, you can map it, so you get access to the pixels, you can copy them from your sensor or whatever API you have for getting pixels, and then you can unmap it. And this is a bit cumbersome, and you see there's a copy here that you might not want to use the input image for anything else, so then you might as well just hand it over to the OpenVX runtime. And this is done by something called create image from handle, which I think we will see later, right, in the more hands-on tutorial. Yeah. So we'll talk a little bit about extensions, I think.
We will have more about extensions later, but I will give some idea about the purpose of them and how they create a certain level of flexibility. So I think you already mentioned a little bit about the idea of the extension, so I will repeat a little bit here. With this one, you can get the compliance flexibility. That means that every vendor maybe doesn't want to have all of those parts into their implementation, so they can choose and pick and say we support this, but not that. So that's one part of the extension thing. Another one is to test ideas. It might not be. It might be a part of a hype or something that you think will be relevant, but you don't know. So you can test it out as a vendor, and then you can discard it later if it doesn't fly the way you wanted. But the core specification doesn't have to change back and forth all the time, so it's stable and reliable. And it's also a way to gradually add to the core specification for those things that really stand the test of time. And so you add to it, but you don't, hopefully never, remove some things from the spec. So you can trust the specification over time as a hardware vendor. And it's a way to add, but sometimes it's also a way to make sure you don't add things. Because this is one example where actually, I think an OpenCL interoperability extension, that's a way to interact between OpenVX and OpenCL to get some of the OpenCL interaction under the hood of OpenVX for some cases. And if you have a platform that doesn't support OpenCL, obviously, it's not possible to have a compliant OpenVX implementation if you require this in the core specification. So that vendor would say, no, I don't want this. And that's okay. It perfectly makes sense. And then, there's this other path of extending towards deep learning, and there's something there that might feel like a bit of a contradiction if you don't when you first look at it, because as we said many times, standard is supposed to evolve slowly and be stable and tested, and deep learning is really, in some sense, the total opposite of that. It moves faster than almost anything I've seen before. So how can we make sense out of that? Is it meaningful to standardize deep learning at all? I would say yes, actually. And I call this a flexifying the standardization. And so you have the core specification, that's really the tested and stable parts. And you find things like convolutions, fully connected layers, activation layers, and so on, several other things. They're really, I mean, convolutions has been around for like 30 years or more. They're not likely to change very much. There might be new versions of convolutions, but the basic convolution is really something that's going to be, it's an old workhorse that's everyone will want to rely on some level. But then, so we have that, and then we have also, it's good to know that because we have the tensor data format in the core specification, you can actually, from the other nodes in the core OpenVX, you can construct certain layers. So, so you don't need to actually put a specific deep learning layer in that extension if it can be constructed from simpler parts. For instance, you might have your own very different way of normalizing some feature vector or some kind of scaling or whatever. I mean, you can easily construct that from other nodes. And then we have the vendor extensions, like we mentioned. That's more of the current hype. The changing parts can be semi-quickly changed. the thing is that you need to have the vendor to implement that, of course. So if you're an application developer, you might not have access to that. But if you're a vendor who want to follow the trend, then you can add it easily. So it's semi-flexible. And then that can, of course, also migrate to the core specification. We mentioned that before. So everything that works and stands the test of time migrates in if it's not contradict certain needs, like the OpenCL thing. And then what if you really want something different and you want it now? You're an application developer, you have no contact with the vendor, and you just want it now. Then you have the user nodes. We had a picture of that before, and so you can use that also for the neural network thing, and you get the flexibility on the application level. And in that sense, you get the true day-to-day flexibility. But in the most basic form, it's executed on the CPU. So that might sound like a big drawback. However, for some operations, I mean, many of those operations that you need that are strange and different, they're usually not that computationally heavy. It's really the convolutions that is the hardest to accelerate. The most of other things are easier. So sometimes that's okay. If it's still not okay, or if you have you have your new convolution operations that you really need to accelerate, or you maybe even have something that is proprietary, you don't want to ever expose it, so you don't want it to be part of the standard. It's your secret sauce. Then that's where the OpenCL interoperability extension comes in. If your platform supports that, you can write OpenCL inside of that user kernel, and you can do almost anything you want because it's very flexible. It might not reach quite the same performance because if you're really implementing towards that specific hardware and you know exactly what you want to do and you know those layer structure, you can usually optimize slightly more. But I mean, it's OpenCL is still pretty good. So for most cases, I think it's going to work quite well. And then if there's another trend, I think we touched this already briefly, that how you actually work with training neural networks and getting them onto the device today. Often, as a developer, you just want to work in the training framework of your favorite choice. It can be TensorFlow, PyTorch, MXNet. There's a whole bunch more. And then when you're done, you have all the control and it's easy to change and so on. When you're done, you just want to have it on the hardware. You don't want to even look at those internal nodes, so you don't even want to have to specify them again. That's where the exchange format comes in. And so if you have an exporter from that training framework, you get it into the NNEF format, and from there you have the importer to OpenVX. And the OpenVX kernel import extension makes it possible for you to import it as an opaque blob that you just access the inputs and outputs and parameters, and you don't need to worry about the rest. And there's in the future there might also be the possibility to have like a limited runtime support in OpenVX, so you can slim it down. If your use case is really all about neural networks, you might not want to have the optical flow node or some of those very advanced nodes implemented. Is a hassle for the hardware developer to have to implement them if they're never going to be used. So we're kind of looking into if this is something that people want. It's not quite there yet, but it might be in the future. Another thing that might come is to be able to. We're talking about this day-to-day application user flexibility. So you might want to be able to extend the import functionality so you can get the user node into that as well, so that you can sort of register your own special layers that didn't exist in the importer that you got from the vendor, so that you could do something really new in TensorFlow, and you define it as an application developer on that side. You define what it means on that hardware yourself, and you sort of register that, so that you can also import it through the NNEF format. The NNEF format typically supports much more than a given vendor will use. So so you extend it, so you can support a bigger subset of what NNEF can describe in terms of network architecture. And so now we have talked a lot about what you can do and what it looks like and so on. We want to return to this graph that we started with, and I hand over to Miko again.
Yeah, so we'll try to just give some inspiration of what you can do with OpenVX and this neural network extension, and yeah, kind of composite small algorithm that you could do. So say you have GDPR coming up in Europe, at least that's a big thing for us. So we have a camera. You might not want to be able to show all the people or the cars, for instance, in the video stream, because that could cost you a lot of money. So you say we have an input frame. We do some pre-processing of that. This could be, you can do some simple traditional computer vision. Maybe you do some image segmentation, right? You do some foreground segmentations to get out some regions of interest that you're interested in. You think these are your these are your objects, and you can update. You can have a background model, which is something you want to display instead of these objects. And then you can have a CNN classifier, your weapon of choice, whatever the latest, greatest. You can use these import extensions to get it into the OpenVX framework, get some object classes out of that, and then we can in-paint the video where we have these dangerous object classes. So we get an output frame that's privacy masked, and you avoid paying 4% of your company's revenue to someone else. So yeah, just a little example of what you can do. So it's really up to you guys. So you can look up the specification and start using OpenVX. It'll be good. And we'll see an example, I think after the break, right? Yeah, so yeah, any questions? I guess you will get a lot more questions when we start using it, and then we're happy to get feedback from everyone using OpenVX. Yeah, thank you.
I have a question on scheduling. So you expect user to implement the scheduling depending upon, user means the provider of the hardware, to implement their own scheduler as how it needs to be executed, right?
Yes.
Okay, so what is the granularity? Is it like, because when you import the nodes like a CNN and things like that, so even the scheduling may have to happen on individual nodes of the CNN and things like that, because there are multiple layers and things like that. So what is the granularity at which you expect this to be implemented, like how it works basically?
That's a good question. I'm not a hardware developer myself, but I mean, that's it's up to the hardware, to the vendor, right? I mean, if you implement very advanced granularity, you can have very optimal performance.
So, but the scheduler is associated with nodes, or
I think
associated with graph, or like where it like.
I think one of the points is that we shouldn't specify that, because it's really up to how you the possibilities of your hardware, how you want to schedule it. You have the specification in terms of the graph, so you have all the information, and it needs to be processed in a certain order given by the graph connections, and then you just choose how smart you want to be, depending on what the options you have.
Yeah, my question is, when the standard provides the hooks, at what granularity levels you are providing the hooks so that the scheduler can be implemented and things like that?
Maybe, yeah. Did you mean these hints that we mentioned as hooks, or
yeah, scheduler basically there is needs to be somewhere you can plug in the scheduler with the standard, like to make it work in the complete flow.
Okay, maybe you mean like pipelining. Then there's a pipelining extension if you want to do it for different frames that can have different. Yeah, so you can utilize your different hardware blocks.
Sure.
That's one level. Otherwise, I mean, the function nodes. You build up your graph using these function nodes, and then it's up to the implementation to figure out. I mean,
it's not that simple, right?
Flows.
Because
of course,
the
it's not
system
simple.
could be very heterogeneous, and the components, like the whole graph, so may not be implemented on one hardware. It may be implemented on multiple different heterogeneous things, and different vendors may have to provide their own scheduler for the component that they are responsible, and everything has to stitch together and it has to work, right?
I'll just say briefly, I think Frank will can extend on that, is you think of it from a developer. Yeah. Hello? Can you guys hear? Okay, I'll try to speak louder. So think of it from a developer who's kind of he has a particular workload, he's going to express it using nodes and data, and then he basically expresses the whole end-to-end workload. And now when an implementer tries to look at it, it's going to look at the whole graph, and it knows what are the inputs, what are the outputs, and the implementer, the hardware vendor, knows what are the different hardware blocks that they have, and they know best how to optimize, taking the whole graph end to end, how to map it where, what's a good way to schedule them, and what time to schedule them, and whether to use pipelining, whatever that is. A hardware vendor knows really more detail about how to optimize. As far as the application developer goes, he's going to say, here is my workload, go figure out how you're going to schedule. So we don't want the developer to be in a position to say, go schedule this part in the DSP, other part run it in another area.
Yeah, that's my concern also. See, the thing is, whole graph is so large, and it's like different parts gets executed on different like a heterogeneous system, right? So I was expecting a central controller. Okay, so now each vendor can provide their own schedulers, but for the entire graph, there is one master scheduler which calls different schedulers when it is executing each node on different hardwares and things like that. It looks like the standard or the open source, the implementation, there is no master scheduler or any framework that controls different parts and things like that. So that was my question basically. Is there something acting more like a master kind of thing?
So I think you use two terms here. First, let me clarify. Node doesn't mean it's one function call that goes into a particular hardware. Node is just an abstract. Let me give an example that Mike was mentioning before. Let's say you have Lucas-Kernadi algorithm you want to run, right? It has multiple pieces running on it now. As an implementer, let's say I have 10 different blocks. I have DSP, ISP, bunch of other ones. I'm going to look at the whole Lucas-Kernadi algorithm. I'm going to split that into pieces. And as a hardware vendor, I know where to execute each piece of Lucas-Kernadi. But as a user goes, user doesn't have to split the whole workload. User simply says, here is Lucas-Kernadi. I just want you to go figure out how you're going to implement underneath. So don't think of node as a unit that has to be scheduled in a single block.
Sure. I'm not thinking of, because node can be combined. I'm more talking about subgraph. So I'm basically saying my hardware can execute a subgraph, a portion of the graph, and I expect scheduling to be taken care by me, but remaining portion of the graph gets executed on a different hardware platform, and maybe I have sourced that IP, I have integrated, and they might have provided me the scheduler for that hardware and things like that. Now, as a system integrator, I need to basically kind of have a master kind of flow controller, basically kind of thing, right? So.
Let me repeat the question the way I understood it. So are you imagining that there is a OpenVX, the whole framework is implemented by multiple vendors. There's an integrator who takes individual blocks and then puts them together. Is it?
That's one possibility. And I was expecting there is a central like scheduler or something, flow controller as part of open source or something like that, which basically takes care of like larger picture into consideration, right?
In terms of direct support in the standard, the way it's modeled is that the scheduler knows about all the hardware resources and knows the capabilities of each one and how long it'll take and what it can run in parallel. So it really kind of has this global view. Now, if you're in the case where you're building an SoC and you're taking IP from different places and they have different capabilities, then you have to work that out. So you do have a global scheduler, and you have to sort of talk to your IP vendor, and they may have their own their scheduler for their bit. So I understand where you're getting at. If you're building an SoC and you're taking IP from all these places, there's not direct support for that in the standard. The standard sort of, again, assumes this, all of the hardware resources and, what they're capable of. But we've done that. I work for an IP vendor. We have done similar things where we talk to the company that is building the SoC, and we have our scheduler where we kind of share the load and that sort of thing. It's not directly supported in the standard, but it's really something that you have to work out with your IP vendors.
Sure. Thank you.
Okay, everyone. Hello. I'm Radha Girduri from AMD. I'm just going to go over the neural network inference with NNEF and OpenVX. So what I'm going to cover is going to be just go over the general neural network ecosystem from inference. You probably have seen this slide before. I think you have seen it already, so I'm just going to brush through it once just to make sure. We got some of the key points noted there. And then I'm going to go over OpenVX tensor and neural network functions because those are the key for this particular session that I'm talking about. And then look at a couple of neural network models out there and how do they map into OpenVX API. Sometimes I'm going to go deep dive into the actual function calls. I may not be able to explain everything, but at least you get, the goal is so that you got some intuition about what it is, and you can go over the actual specification document, some of the tutorials online to kind of fill in the blanks there. And we'll look at the NNEF-based inference workflow, and we got a couple of open source tools, what all you can use, and then we'll do a hands-on session. Well, hands-on by mean, I'm just going to go through the actual exercise, typing in here so you can see what's happening on the real machine there. So starting, I think you have seen this diagram where on the left side, you have the training frameworks, which kind of starts with your problem definition. And the part that is important here is you have several frameworks producing several different data formats, and you've seen about NNEF being at the center. And once you have NNEF, then there are several inference engines out there, and then being able to abstract that, we created this OpenVX API, and a lot of these OpenVX implementers might be able to extend it using OpenCL. In fact, an application may be able to extend it too using OpenCL for any specific corner cases that may have, or maybe if they want to do some pre-processing of the data, or even post-processing, they could use OpenVX or certain OpenVX extensions, user kernels, to be able to do that. The goal always here is to be able to get the functionality on diverse inferencing accelerators out there, right? So with that, let's start looking at the TensorFlow object. Basically, tensor is basically a multi-dimensional array. Now in OpenVX case, we support at least 4. That is kind of mandated that every implementation supports at least 4. So most of the networks, we don't use more than 4, but this is just to make sure if somebody comes up with a new architecture that needs more than 4, they can support it. They can request for that. A vendor is free to implement those. We don't want to restrict an implementation. So one thing key to understand in a specification especially is we only give the minimum set of functions that needs to be implemented. We won't say an implementation should not do or cannot do that. Those kind of words, you won't see it. We only say minimal form factor. For example, tensors, we say you got to support up to 4. That means every implementer will support tensors up to 4-dimensional. So here is one way to visualize these dimensions, these tensors. You can have a 1D tensor, let's say in this particular case as a 6-element. It could be a 8-bit integer or 16-bit, or a vendor might be able to extend to whichever type that they may have. And you can consider that as a vector. It's 1D tensor is nothing but a vector, one-dimensional vector. And then you can look at 2D tensor, which is like a matrix. You can kind of see 2 by 2 kind of an image. You can consider image as a 2D tensor in one way. But in OpenVX, we have explicitly defined a data type called VX tensor. This is just an abstract type. When you say VX tensor, you're basically expressing what is the number of dimensions in the tensor and what are each dimension it is. And how it gets mapped to the hardware, how it gets internally by an implementation is up to the implementation, but a developer can simply say, here is the type of object that I want, and here are the meta parameters for that particular object. Right? And you can similarly see 3D tensor and 4D tensor. Kind of put 4D tensor as block of 3D, so it kind of makes it easy to visualize. And you can also visualize it as a batch of 3D tensors. Right? Now, when it comes to the data types, I mentioned about various kind of data types that a vendor can choose to implement. So what does standard specify as a normative is every vendor have to support 8-bit, unsigned 8-bit, or int 8-bit, and with kind of fixed point, but there is kind of fractional parts are kind of 0 bits. And another one is int 16, where it has 8-bit fraction. So you kind of look at it, and 8-bit, you can basically say it is Q 8.0, if you're kind of used to that notation. And if you look at int 16, it is Q 8.8, so you have 8 bits fraction. Now, standard does not restrict what kind of different tensors are there. We kind of specify what are the mandatory ones that one need to support. And typically, if you look at float, since code specification, sorry for that. Since the course, man. Forgive me. Okay. So the core specification doesn't give floats, but vendor is free to extend it. At least we in our case we have GPUs, so we would love to use floating points. We extend it, but if you look at low power devices, they won't have the luxury. So at a specification level, we try to specify whatever that every vendor can implement in the markets that are kind of targeting. So that's going to be the common denominator. That's what the standard specifies here. Now let's look at some of the APIs that you have to create a tensor. How do they look? So for tensor creation, there's a function called VX create tensor, where you kind of specify context that you've seen it in Michael's presentation. And you specify number of dimensions. It could be 1, 2, 3, or 4. And then you specify the actual dimensions as kind of list of these dimensions. And then you specify data type. So we have very well-defined enums for data types, whether it is 8-bit or 16-bit, even 32-bit, all the kind of data types that are kind of most commonly used. You have those data types. And then tensor also takes the fixed point position, right? For example, for 16-bit, you can say 8 bits are fractional. If it is 8-bit, you say fractional position is kind of 0. And you have a lot of flexibility. A vendor can now extend it to, let's say if they have 8-bit data type, but they have fractional bits to be 4. The API is general enough, but the spec requires that every vendor support these 3 data types out there. And once you think the data tensor object is not needed anymore, you just call VX release tensor, and you give a pointer to the tensor object. The reason we give a pointer is the release basically resets the pointer to 0. That's kind of implementation detail, but that kind of makes it a lot easier to avoid errors in an implementation. It's kind of to ease the developer in there. And you can kind of see this VX create object type and release object type. That's kind of common across all the objects that we have. I went through this one. So one thing key I want to mention, this is if it's 4-dimensional, the standard way to specify is first one, index 0 of the array is width, index 1 is going to be height, then channels and batches. And if you are used to cafe kind of notation where you give the first one is batch, second one is channels and height and width. So here we're kind of using the standard C model where 0 is kind of, you're going from lower dimension to the higher dimension. So that's one thing you get used to. It was hard for me itself when I started this. So here is a simple example. I'm not sure. I think this is, so basically you can take an input image coming through. You can do multiple feature maps, which are basically convolutions going through. So if you look at the particular part where it takes the 4D 224 by 224 with 3 channels, this is kind of an RGB image. You kind of represent that in a 4D dimension, depending on number of batches you have. And once you run the feature maps, you need some kind of an intermediate representation to keep the output, the virtual tensors that Nicholas and Michael mentioned. You can create a VX create virtual tensor to represent these intermediate results. Again, output for this particular network is a 2D, which basically has the final output with number of classes and softmax output, which says what's the chance that it's a cat or a dog scenario, right? Okay. I mentioned about the virtual tensor there. And there's also, once you create an object, you can also query the attributes of an object. So you can take a tensor object, and then you can say what are the number of dimensions, what is the data type, fixed point. So this is just a general API. If you have created already, you want to query it in later part of another function, you have an API to be able to do that. So how do we, once you created a tensor object and an implementation is free to choose where it's going to allocate it physically. It may not even allocate a buffer until it needs it. So it's up to the implementation detail. So as soon as you create an object, it notes that, okay, such a tensor is needed with those dimensions. Now, once you create a tensor, you ran through running a graph, you want to look at the output, or you want at the beginning, you want to kind of copy data into the tensor. You need to use copy or map. You've seen that in the earlier presentation. So there is an API called copy tensor patch. You can access a part of a tensor. We call it kind of a patch. So all you specify is, again, you specify what is the starting point of a tensor. You can see the diagram on the bottom right. Let's say I want to kind of pick a small 3-dimensional piece here. So you can specify where does the 0th dimension start, where does it end, similarly for every other dimension. So at the end, you basically get a patch of a tensor. Now you can specify user pointer where to copy it to or where to copy it from. You can specify the stride of each dimension. Okay, it can take forever talking about this, but I think it's kind of, the general concept is you can copy from a user pointer. Now, if this memory on the tensor is, let's say, sitting on local memory of a DSP or a local memory sitting on a GPU, wherever it is, it's kind of abstracted. When you call copy, underlying hardware will figure out how to copy it, whether to use DMA, right? All that is implementation detail, but from an developer perspective, it's kind of very simple. You just call this copy, magic happens underneath, right? Now, what are some of the basic tensor operations out there? So just giving a tensor object is not useful, right? So in the core spec, we did define certain basic tensor operations that every vendor has to implement, which is like, element-wise, you can do addition, subtraction, multiplication, convert depth. Let's say if you have a 16-bit tensor, you want to convert it to 8-bit or vice versa. So you have a standard function call to be able to convert back and forth. And there's also table lookup. Table lookup is if you have some kind of a nonlinearity, you can't express it using any of the standard functions out there. You can just create a lookup table. Let's say you want to go from 8-bit to 16-bit, and you want to do some kind of a logarithmic or some kind of a crazy function. You could kind of give the mapping from 8-bit to 16-bit, and you pass that to the tensor table lookup node. It'll take care of doing that conversion. And that conversion can be done differently depending on each hardware out there. So the way what table lookup takes a lookup table object. You create a lookup table object, pass it to the node, and underneath, hardware knows how to represent that inside their hardware, right? Now there are certain other functions such as transpose. You kind of know if you want to kind of flip between, if you want to do NCHW to NHWC, if you need some kind of a conversion like that, you can use the transport node to flip the accesses between them. And there's a standard matrix multiply, and you can pretty much represent any of the neural networks using matrix multiply, but you may not get the best performance. That's where you want to use convolution or even LSTM if it's custom one. Right? I mentioned about this. Like I said, other formats can be represented by the vendor. So now let's briefly go over the neural network extension. You've seen this in the previous presentation. We basically defined 8 layers nodes here. So one is the activation. It supports a lot of activation, ReLU, soft ReLU, sigmoid, 10H. We have a lot of these variations in there. It basically takes that activation as an enumeration. And basically the activation layer is a placeholder for representing all this. And convolution layer, a standard convolution layer, deconvolution layer, fully connected layer, normalization. And in this particular case, normalization is LRN node. And you have a pooling, which can be max pooling or average pooling. It takes it as an enum, right? A vendor should be able to extend it if there is like min pooling or some other crazy pooling they want to. And there's softmax and ROI pooling. These are the 8 functions. You can pretty much represent most of the standard networks using just these APIs. And I just want to mention briefly one thing that is, LSTM is a very tricky one. You can represent with these nodes, but most of the hardware vendors, even like the frameworks, they tend to define LSTM as a separate node. Again, it comes down to what way you can get performance out of. Some hardware vendors say, well, I can, even if you specify it as a matrix multiply, I can figure out how to implement it. So right now in the specification, we don't have an LSTM node in the current extension. We could add it sometime later, depending on the feedback we get from the community in there. There was some question earlier about conformance tests. So this is something I want to mention briefly. When it comes to neural network, it's going to be hard to say when you give a convolution, everything is 8-bit as input. Let's say everything is 16-bit input, output is going to be 16-bit. What is the precision? There are a lot of different approximations how they compute the convolution. So what we specify, instead of specifying each layer the accuracy, we kind of put some tolerance, depending on, some implementation might use some kind of a tensor compression. They might make some approximations there. It's going to be hard to come up with a standard that is suitable for every vertical market or every hardware vendor architecture. So what we did is we kind of defined certain tolerance. And if you need much stronger tolerance than that, if you need much lesser than, it's kind of you got to work with the particular vendor. But we do guarantee certainly if anybody says they support OpenVX neural network extension, you can be guaranteed that error is going to be within this range, right? This error is much, much below than the error you get in the accuracy you get when running the whole network, right? One example is, if it is cat with a probability of 0.8, you're going to be, that's a lot of error compared to the error you see here in the computation part. So I want to take a couple of examples of at least part of the networks and see how we can map that into OpenVX APIs. So here is an example. This is just a small part of ResNet. You can see whether it is ResNet 50 or 101 or 152, whichever one. You have this residual block in there. What it basically takes is input is a tensor. It could be pretty much long. You can think of it as a 4-dimensional. And then you're running through a convolution. This picture, I picked it from the original paper, so the wording is not accurate. When it says weight layer, you can pretty much think of it as a convolution that takes weight as an input. And basically, in addition to just passing an input tensor, it also takes a weight tensor on the side somewhere, so which is going to be a constant since this is an inference case. And after doing a convolution, actually, let me mention a couple of more things. The convolution, not just a convolution, it might even take a bias. It might have a bias optionally, right? And once in this particular example, after it does the convolution, there is a ReLU, which is a kind of an activation followed by that. And there is, again, another convolution and bias added to that. So one thing tricky in the residual networks, if you're not familiar with it, is it kind of performs this convolution. It's a two convolution, and then takes the original input, adds it at the end. And that's what is the trick that they used in the residual network when they come up with. And that is one of the key advantages of ResNet, how it achieves the very good performance out of it. Now let's try to see what functions do we need in terms of API to be able to map this residual block into OpenVX. So basically you call convolution wherever there is a weight layer, and convolution takes bias as an optional. If you pass the bias tensor as null, it kind of thinks that you don't need to use bias. It just does the convolution in there. And then activation, in this particular case, you pass activation enum as ReLU. And at the end, where you see the plus, that is where you basically do a tensor add. It's kind of taking two tensors, and these two tensors will have the same dimensions in that particular case. If the dimensions are different, and you can't add element-wise additions, so you will see during the graph compilation, you'll see an error saying I cannot verify the graph because the dimensions are not matching in that particular case. Right? So I'm going to dig to, this is something I made up just so that you kind of a good discussion point to look at. If you take something like LSTM, how can somebody can just take that LSTM, represent it using existing functions. Now, if I'm a vendor, I would like to implement LSTM separately as a block because I know how to optimize the whole LSTM block. So on the right, what you see is the actual equation that happens underneath the LSTM block. So I just took the forward path because all the, you can see that input weights, recurrent weights, peephole weights, and then bias weights, they're all going to be constant. So beauty about they being constant is a vendor can look at those, they can reformat it any way they want for their implementation, for their hardware, and then use them because they're fixed. They can do lot of optimizations under the hood for these kind of weights. And you can see there are a lot of weights here. They're about what? 14 14 different tensors as weights there. And you can see the equations below. You have z, t, which basically weights times the input xt plus r times the previous output. I'm not going to keep going through the full details, but you can kind of see there's a complex set of functions that are happening. And there are activations too when you see g and then kind of a rho. One is a sigmoid, the other one is kind of a tan h function. Those are kind of two activations in there. So if you look at the whole recurrent LSTM example, you can kind of see the input is coming from the top, and the t, the t represents that at the present time, and the t minus 1 represent the state of it in the previous iteration. So kind of recurrent means it's kind of going in cycles. You give an input, you get an output, and that internal stage will get reused in the for the next input that is coming through. This is what gets used when you're doing a lot of this speech processing, speech recognition part. It gets used even translation, machine translation. This particular LSTM is very popular. Somebody told me once, if you look at what networks get deployed most, LSTM is number one. I don't have data to prove it, but I think I take that word from the expert in that field. So in this particular case, you can see t minus 1 is the internal state from the previous, and then it computes the current one. And y is an output, and that output also, it keeps a copy from the previous iteration. So representing this in OpenVX is a little tricky thing. So how do we represent the current state versus previous state, doing that swap? That's a good one. Means it's a little bit tricky since you haven't seen an example before if you're new to this. So we have an object called VX delay object, which is designed specifically for this purpose, but we designed it long back before neural networks came in. That comes very handy here. And you can create a set of buffers using delay, and then you have an API to say every time I use it, automatically flip the buffers in the delay object. So let's quickly go over. This is just one slide. I had passed one. I just borrowed here. So what is a delay object? You can think of as an index as a time. 0 being current time, minus 1 being t minus 1, t minus 2, like that, going all the way to t minus n plus 1. So you can create a delay object from any of the existing objects, any kind of other objects. It could be a delay of images, pyramids, matrices, or tensor objects. So in this particular example, what we're going to use is going to be a tensor because we need current and the previous values. That means the number of objects in the delay element are going to be 2, right? And one more thing I got to mention is a reference object. Reference is just like, I don't want to use void star, but it's pretty much, it's kind of a base class. You can think of it as in the class of hierarchies. It's kind of, we have a, in one way, OpenVX uses the object-oriented method, though we don't use C++. You can think of reference as a base class of all other objects. That means you can take an image or a tensor or anything, you can cast it to reference. You get certain APIs that work specifically for the reference. And that reference will still contain the data about what the original object type is, so you should be able to extract it. If you know that it's an image object, you should be able to cast it back to image, VX image. If you know it's a tensor object, you can map it back to a tensor object and then keep using it, right? So here is a simple example. You can basically create a tensor. I'm just going to call it exemplar because it kind of defines what it is. It just carries the metadata of the object. Then you're calling a VX create delay. You pass the exemplar. You say, I just need 2 because I have 1 for the current and 1 for the previous one. The moment you create a delay, you know that exemplar is not needed anymore. So all the data that is passed in the exemplar gets kept inside the delay object. Or if it needs, it will keep a reference count. It keeps a copy of it, or it keeps a reference of that object. So when you say release an object, doesn't mean it just destroyed in memory. Don't think of it as a free call. It's just that it keeps a count of all the references. When none of the objects are needed anymore, that time the actual allocation, freeing up the memory happens. Again, that's all defined by it's up to the implementation, right? How they do it. And then if you want to access a particular element in the reference, you have an API called VX get reference from delay. You specify the delay, say 0, which is current time, or -1 means t minus 1, it gets you an object. Since it gets a reference, you know it is a tensor object, you can freely cast it to a tensor. And then VX age delay basically says, when you say age delay, it kind of comes from circuits, right? When you say delay, whatever is 0 will become -1 after you make that API. And the 0 will be kind of some data. Most of the implementations will use whatever is -1, they flip it back to 0. You can think of it as a ring buffer. But by the specification, once you call age delay, the 0 index is going to be undefined. That means you can't assume that the last one you have is the same data that you got it at 0, right? So it doesn't. This is just to make implementations have flexibility to do whatever they want underneath to get optimizations. So if you look at LSTM now, so you can kind of see there's a delay element I used for CT and YT. So it's kind of another way to represent it. And the C ones are just the internal state, whereas the YT is an output, XT is an input. So kind of LSTM takes care of that internally in there. Well, let's just see what are the different existing neural network extensions that you could use to implement it. If you look on the right, you see there are a lot of matrix multiplies. You can see there are 8 matrix multiplies, and then there are element-wise multiplications. If you see dot in a circle, that's basically an element-wise multiply. You can use the tensor multiply node, which is kind of element-wise multiplications. There are 6 of them, and you have 4 add nodes and then 5 activations node. That's all it takes to represent it, right? Now, once you represent it, an implementation will look to see how they can optimize. Can they combine these matrix multiplies? It's up to the implementation, how they're going to do it. So I kind of took just the subgraph, just the input gate part, and say how the graph is going to look. Kind of defined it just so that you get a glimpse of how it looks in there. I'm going to skip quickly because we could spend more time on the real exercise. So here is an example of VGG16 model. You can see it has a lot of convolutions happening in there. I think 16 comes from because it has 16 layers for the convolution. You can see it starts with a bigger image and starts going down all the way to 1,000 because it's trying to classify 1,000 different kind of objects in there. And what are the different layers? What are the different APIs? One needs to represent VGG. You need a convolution, activation, pooling, fully connected, and softmax. That's it. With those 5 calls, you can represent the whole VGG network. So now let's try to look at the complete inference workflow. Now kind of you understood what are the different APIs, how to map a model into the APIs that are there in the core as well as the neural network extension. Let's see how we can deal with the end-to-end workflow. You've seen this diagram several times, so by now I think you probably memorized the part. So in this particular case, we're going to look at TensorFlow. It could be anything. It could be Caffe. It could be Onyx, whatever that is. We want to first convert that into NNEF. The goal is to have a common exchange format that we can get and see how we can take that NNEF and generate a subgraph, or basically it could be whole graph, a sequence of APIs that we can use to construct that subgraph. You can see the previous examples that you have seen, those kind of set of APIs, and creating these intermediate nodes, how to connect them. That's what we're going to look at. And in this particular case, we picked VGG16, a pre-trained TensorFlow model that we picked from the TensorFlow Zoo, right? Yeah, a lot of work is done by Chaitanya, so I have to thank him for that. And the first part is we're going to convert it to NNEF, and once we have NNEF container, we can, basically in this particular demo, we're going to generate OpenVX code. It's going to be a C code that builds a graph from the NNEF container. And then all we're going to do is use that C code to build the library and a small application on top. All it does is takes an input tensor, runs the graph, spits out an output, which is going to be softmax output. Then the way we're going to do that is we're going to take a JPEG image, and then we're going to convert that into a tensor. We're going to feed that to the network. And then when we get a softmax, we just wrote a simple utility that goes through the softmax output and say, okay, which is the highly likely one? And then we're going to say, well, whatever that object is. Okay. Couple of things I want to mention here in terms of the open source tool. We kind of used almost whatever we're using here are all open source tools. So this is something you have seen coming from Peter's Mechanism slides. We have NNEF tools which contains the converters that go from TensorFlow Cafe into NNEF. And whatever we're going to post in later, other ones that are in development will also appear onto the same repo here. So we're going to be using converter / TensorFlow. That's a subfolder what we're going to use. There's a script there that we're going to use. One thing you got to note is the current implementation for the converter requires that you have a TensorFlow installation on your machine. In the next version that we're going to be releasing, we're going to remove that dependency of TensorFlow so that it goes directly from just parsing the TensorFlow protobuf and go all the way to NNEF. So kind of container to container, so you don't have to worry of installing TensorFlow completely on it. And the next one is going to be for generating, this is AMD's open source implementation. We open sourced it just to promote the standard, and we got an early prototype. We thought it's good to get it out and people play with it. And I got several contributions coming from a lot of interns, and it's really good for me to start using it. We've been using this for tutorials to make it easy. And in this particular case, there is a folder called util/inference generator, which basically can take a cafe model and generate a OpenVX code or NNEF to OpenVX code, and we're going to use NNEF to OpenVX code in this particular exercise. And we have several examples. I think we've been doing these tutorials from 2015. We started with CVPR, and it's been done by a lot of working group members, and there's a lot of contribution that went on, and I kind of pulled up all those exercises that we did, pulled that into a GitHub. You can see at the bottom OpenVX_tutorial. I would like you guys to, if you want to try some examples, that they have in that particular website, you got 3 examples, 3 exercises. You could use those. It kind of gives you step by step. You can go through if you want to understand how to actually do. Let's say Lucas Canada example that Mikhail has mentioned. You have an exercise for that. It gives you step by step how to write each step of the code. I would highly recommend trying that one. If you see a problem, please post a question on that issue, and I've seen a lot of other people contributing and responding to those questions. I have to thank several folks for this particular project from the Khronos working group. So just want to move to the next step of going through the walkthrough, and Chaitanya just told me he has posted example and the instructions. Not yet? Okay, we're going to post it after this tutorial. What are the walkthrough? We're going to do all the instructions there. So if you want to try it out yourself, you can do it after this workshop is over. So let me switch to the exercise. So the first part we're going to be showing is, so he has installed TensorFlow. So this laptop is actually connected to a machine. Back there is a Linux box that has, AMD's GPU. But in theory, this is all based on OpenCL, most of it, and underneath we're using one MIOpen. But in theory, if you have a OpenVX implementation, you should be able to just use the same exercise that we're doing. You just need a good OpenVX implementation underneath to be able to do this exercise. So he has installed for this exercise, install TensorFlow. It's very easy to install. Once you have a Linux box, you simply call pip install TensorFlow. Just one command. Google has done a great job of getting everything installed. That's the only dependency we have. So the first part he's going to do is he downloaded VGG16. Can we Google that and get the VGG16? Yes. Yeah, so you can just Google VGG16 TensorFlow Zoo. I guess if you do that, you'll find it on the website.
I'll keep a link on wiki page in OpenVX tutorials soon.
Okay, so you'll find a link to that. So he has downloaded it. Now, first thing he's going to do is convert TensorFlow model into NNEF. Okay.
So to this, I made a small example on NNEF tools, which exports VGG16 TensorFlow model to NNEF model. So I took a small example from NNEF tools, which already has a ResNet 50 example. I made a small example on VGG16 taking on top of that one. So it takes a checkpoint file right now, TensorFlow checkpoint file, and it takes an input shape, and it takes a placeholder for an input, and then converts into an NNEF file. So I'm going to quickly run VGG16 example. I have already pre-downloaded the TensorFlow model.
Can you tell us what is CKPT file is?
So CKPT file is nothing but it's a TensorFlow checkpoint file. It takes a checkpoint. This application takes a checkpoint file, tries to convert into NNEF format. So it is right now converting, and it has converted. So you can see the checkpoint NNEF file in the folder where the checkpoint file is present. So I'm quickly go to that folder. So it has generated two folders, VGG16 NNEF and VGG16 activations. So VGG16 NNEF contains the NNEF format of the VGG16 network. So the graph.nnef contains the textual format of NNEF of VGG16. So this is the format.
Let me go over this quickly. So this is the structure file that Peter was mentioning. It's kind of a text file, and it kind of specifies what version of NNEF it is. And then there is a network graph which basically takes an input and output. These input and output are tensors, right? And we have to explicitly say that input actually is coming from external, and then specify the dimensions and what are the metadata that corresponds to that. So one thing you notice here is for input we say external shape equal to 1, 3, 224, 224. The order of these values are different than what I mentioned at OpenVX. And this that's reason this order is picked is because we want to be able to, in NNEF, being able to scale from 2-dimensional to 4 dimensions. We want to keep the first dimensions as the batch. That's one of the reasons why we kept this here, and then channels, and all the lower dimensions such, height, weight, or whatever other dimensions come in are going to be the lower ones that to the right. So to the right is the lower one, to the left is the higher one in terms of dimensions. So just a notation here. And you can see what are the variables. Variables are nothing but your weights. You can say what are the constants you have in the inference model. So when you have a convolution, you have the first one is kernel 1, which is nothing but the weights that get fed to the convolution. Bias 1 is the fixed constant biases that gets fed to the convolution. Now let's go at the convolution 1. And one more thing I want to mention, how all these names come exactly from whatever is referred in the TensorFlow model. So these names are not something the converter made up. Whatever the input tensor has, those names come here. If it has very lengthy names, it's going to be hard to read. Luckily, VGG16 had very easy names for us to walk through the code here. So you can see there's a convolution which takes input, specifies the kernel 1, which is the weights and biases, and it can also specify the padding. In this particular case, no padding is needed. You can specify the border mode, whether it's a constant or a couple of other modes, and then you can specify the stride and dilation there too. What else do I need to say? Now, let me say one more thing about the kernel. For the kernel, you see there is a shape that's easy to understand. There's a label. Now, what label specifies is what is the name of the binary file, or maybe you can say it's more like a path to the binary file in the container. So let me introduce the word container. NNEF is basically a container. It's like you can think of it as a folder or it could be zip file, whatever the container that you use. It basically contain multiple files within that container. It comes with a whole group. You can't just tear apart the pieces and call it NNEF. You got to put everything together in that container. That whole container is called, you have to use the whole container to claim it's an NNEF. So in this particular case, for the kernel 1, the weights are going to be under the folder VGG16, convolution 1, convolution 1, underscore 1, and kernel 1. So if you walk through that path in the actual container, you will see there's a .dat file that has all the weights going in there. What else do I have to say? Okay, one more thing for convolution 1. You see the input dimensions are clear, but the output dimensions of the convolution 1, which is the output tensor, the dimensions are not specified in the structure. The document specifies the relation between input tensor dimensions and output tensor dimensions. So in one way, you can kind of see convolution 1 as an intermediate or a virtual tensor if you try to map the terminology to OpenVX. And what else I should say? That's it. And ReLU is just an activation. You can kind of see same structure going all the way down. And the one thing important is the output is the name of an output. So if you look at the graph network, in the first parenthesis, you can have list of input tensor names, and you have an arrow followed by list of output tensor's name. The reason we define that is it's kind of, somebody might be able to define a network or maybe define multiple networks in the same graph, being able to run that. So it gives you that flexibility. Luckily, VGG has only one input and one output. It's easy to explain here. Can you scroll down all the way to the bottom? Yeah, you can see the last one is output. That name you have to mention in the output list. That's why NNEF knows that's the output, because you might have multiple outputs in there, and you might use actually one of these output as an input to further network. So you need to kind of clearly identify what tensors are outputs and what tensors are inputs. Right? I'll give it back to you.
So the next step for this exercise is to run NNEF graph on an open source inference engine. For this one, I took an AMD OVX modules implementation of a neural network extension. So I have already cloned the modules directory here. So I'm gonna quickly install the library.
Why don't you show the tool that takes the NNEF to convert that into, are you showing that?
Yes, yes.
Okay.
So I'll install first and then.
Okay.
So there is a tool which converts NNEF to OpenVX C code. So I'm going to quickly run this NNEF to OpenVX C code. So it takes a NNEF folder and it converts into an OpenVX folder which contains the C code of OpenVX. So I have loaded the NNEF folder, and I'm naming a folder as OpenVX underscore VGG16. So this generates like couple of files, weights.bin, some couple of C++ files, and a CMake file.
Why don't you go through the header file first?
Okay.
This is too much detail. I think
Okay.
header file is good enough for the audience here. So what this code generator does is just creates one library, so CPP and .h file, and the kind of weights that you kind of pass it to. So it basically gives you one function, which called, in this particular case, called ANN add to graph. So where you specify a graph and you specify an input tensor and output tensor and you give a binary file, all it basically implements is once you give a graph, it just inserts a subgraph. And for the subgraph, you're specifying the input tensor and the output tensor in this particular case. If you happen to have in the NNEF file multiple inputs and multiple outputs, you would see the signature changing. You would see VX tensor, let's say input 1, comma, VX tensor input 2. The signature will keep changing. At the end, always it's going to have a name of the binary file, right? And so the ANN modules.cpp will have nothing but just how to connect all these nodes, that list that you've seen in the on a NNEF implementation. You would see line by line correspondence there. And this comment is just for so that you understand what this implementation corresponds to, input dimensions and output dimensions. Why don't you open the .cpp so that we can see at least one. Yeah, just skip the first function, initialize function. So you can use this way. Yeah, so you can kind of see here there's it tries to get a context and try to get the dimensions. You can see there are intermediate variables it's trying to create. Well, it's trying to create all the tensors for the weights. And you can see the kernel 1 dimensions are 3 by 3 by 64. And 64 is the number of output channels, I guess, here. And then it's kind of creating a tensor object. And that ignore the macro. It's trying to look to see whether object creation is successful or not. If you go further down, can you press Control F? Just keep, okay, let me take all this, right? Once it created all the tensors that are for the weights and biases, all the constant values, then it's going to initialize them. The way it initializes is, it opens that binary weights file that we created. It just goes one at a time and try to initialize each of the tensor. And initializing just means that you're using the VX copy tensor call. Open the file, read a blob of it, copy it into the tensor. That's all it does. Very simple function there. You can actually, when you generate it, you can look at the final code coming in there. It's kind of initializing all the tensors that are constants here. You can kind of see that. And added a check just for sanity, so that program won't crash if I give something bad. Checks to see that weights file is what it is using here. Now I'm just going to go through just one part here for the graph. How does it create the first convolution layer and ReLU layer? So the API here is first, the output of convolution is a convolution 1, which is kind of an intermediate variable. So you could use the virtual tensor object. Have you seen that in the example Michael has mentioned? So in this particular case, we're going to use virtual tensor. You specify number of dimensions as 4 and specify all the dimension. And yeah, please don't panic when you see float 32, because that's what I have in my implementation. My working group guys always get panic when they see float 32. But in future, when we have a hardware that supports int 16, we'll try to switch to that. Right now, this is what we have to show the end-to-end workflow. And once you create that virtual, so now the convolution layer takes a data structure for all the parameters, like for example, padding or dilation, what is the outflow policy and rounding policy, and downscale mode. So basically, whatever the NNEF parameters are, we got to map it down to the OpenVX parameters. And if you look at dilation, the way OpenVX defines dilation 0 means don't dilate. In NNEF, you specify dilation as 1. So kind of we have to convert from one domain to the other, a lot of these parameters. And if you look at overflow policy and rounding, well, overflow is kind of easy to say, it's saturate. Rounding policy near to even, which is kind of common in floating point. They are important for the fixed point implementations more than floating point, so we kind of ignore that. It's as good as not mentioning in kinds of floating point. And then you can see convolution layer. It basically takes, you basically saying input, weight, and bias, and you pass all the convolution parameters, and the output tensor is going to be convolution 1. And if you look at the next line, after creating the convolution is a release node. How can we just create a node and release the node immediately? The reason for that, I think I mentioned before, is OpenVX keeps track of how many times an object is in use. So when I create an object, I got a handle for the node, right? At the same time, since that object is created in the context of a graph, graph also has a copy or basically a reference to that particular node. So if I release from a user profile, if I don't need a particular object, I simply release that one. Since the graph already has a reference, that object won't be gone. It won't disappear. It's still there. When you release the graph, then graph says, I don't need that node anymore, then the whole node object goes away. So you have to kind of think it that from that perspective. And it has, you can use that trick for doing a lot of optimizations. If you don't need some buffers, you can release it. Underneath implementation can look at that saying, okay, now I know user don't have this object, which just means that I can do whatever I want. I can just not even allocate that buffer. And it's any special optimizations they could do. So once you have that, you can see the ReLU is kind of a activation. You can see the enum there. From going from convolution 1 to ReLU 1, you see activation underscore ReLU, where you're specifying what activation to run. And that's pretty much it. Just goes line by line translation to all the way to the down. If you don't have any questions, we'll skip to the next one. Okay, good night.
So now I'm going to take an image.
Maybe you should go over ANN test too.
Okay.
Skip to the functions. Okay. I'm going to skip a couple of them. These are just for, so you can see kind of a main function which takes the weights and the input and output file names. If you want to kind of feed in input and output tensors from a file, just kind of easy to test. So you can see it creates a context. And you saw that in the introduction slides here. Then it creates an input tensor with 224, 224. And then it creates an output tensor, which has basically 1,000 different classes in there. And once you're done, all you do is, you can see there is a create graph. We're building a graph module comment. You see that? It tries to create a graph, and there's VX status call. Let's not go into the detail. Once you create a graph, all you're doing is add graph to, you're basically calling this API that we built, just the library that we built. All it does is takes a graph, instantiate the subgraph that corresponds to the neural network, and once the graph is done, then you can do verify graph. Now, the trick here is, let's say if you have some pre-processing happening, if you want to take an image, do some pre-processing, you could insert all those nodes before instantiating the graph module there. And once it is done, it's basically going to call process graph, and it kind of loaded the input, it saves the output. That's it, yeah.
Can you open the image?
Just run through the flow at the end, you can show.
Okay.
Yes. Sorry, I'm going slow because I have enough time.
So I'm going to run this application now. So before, firstly, I'll take an image, load it into this AND test, and try to get an output tensor. And then I created a script which takes this output tensor and gives you an argmax output. So argmax output gives you the label which out of 1,000 you can find what image is it. So
You can see this code generator also generates a CMake file, just to simplify our job. Every time we don't want to create a new CMake manually.
So I'm quickly installing the application. So before this one, we need to convert an image into a tensor object. So for this one, I wrote a simple script that converts an image into an input tensor. So I already have that input tensor. So I'm just running that input tensor. So this application now converts into an output tensor. So I'm going to quickly go to an argmax script, which takes this output tensor and a labels.txt file, which contains all the 1000 labels. So I gave a small bus image, and it showed the classification as a minibus.
Yeah, we didn't show you JPEG. You got to trust us right now.
Yeah.
Yeah, we can. I think he took a couple of images. All three were producing, but it's just a floating point, so you can't expect anything worse than that. So that's it, right? You have anything else? Yeah. Okay, that's perfect. So he's going to add all these instructions to the GitHub page. And I would love you guys to just contribute more. So if you have any questions, we have a couple of minutes left.
When you were talking about the layer the functions for APIs for different layer types, I was curious to know if the convolution, for example, it did not seem to be able to do any other forms of convolution like depthwise or any other sort of things. So what's the strategy in general to add more layer APIs? Would it be adding enums to convolution, for example, saying convolution of this kind, like pointwise or depthwise and so on, or it would be exclusive kernel APIs that are going to be added to the list?
So let me make sure I understand that. So when you say different kind of convolutions, can you repeat that part?
Let's say depthwise convolutions.
Depthwise convolutions.
So this API wouldn't support depthwise for now,
okay.
I would imagine. So if you wanted to add that to the set of APIs, would it be a new API or it would be an enum, for example?
So right now, the way we defined it, if that's not covered in this function, we don't have a placeholder for enum. So I'm going to tell you. So once we define an API, we can change it to the extent that existing applications are going to fail. So in this particular case, depth convolution is going to be another API that we're going to be creating. So the process in which we're going to be creating is, if you have a depth convolution, if you think that's a need, you can bring it to Khronos. We'll try to extend it. The existing one, maybe we'll make a revision 1.1. We'll try to add that functionality. Yeah, so all those are possible. So we have resources, Khronos page. I would like to have that discussion going on in there. Yeah, okay. We'd like to hear that feedback.
And another question was with this add to graph kind of API, which took one input and one output. But in general, how would you plan to scale it for multiple input, multiple output graphs?
Okay, so firstly, add to graph is not an API from Khronos. That's something,
just a utility.
toy example made that up, right? So what it does is actually from the NNEF. NNEF tells you how many inputs those are and how many outputs those are. It gives you the names. All this is doing is translating. You can pretty much think of it as translating line by line on NNEF into C code. Mm-hmm. Convolution is basically one line gets converted to, let's say, 5-6 lines, right? Input tensor is input tensors. If you have multiple tensors, it tries to create multiple tensors in the code. Yeah.
So the graph in general is flexible enough to support multiple input graphs as well as generate multiple outputs for
localization. So you could even have in NNEF, let's say, you have 2 networks running back to back, right? And you have an intermediate stage. you want to look at the output of the first one, in the middle one, as well as the last one. You could say those two as in the output list.
Okay.
So you basically pretty much get the same data.
So you can mark them as external and get those outputs, extract them?
Yes, yeah.
Okay.
And also, you could have multiple networks in parallel happening there too. I could have a network. Basically, everything becomes a subgraph.
Okay, thank you.
It's basically graph. Okay? Whatever you can represent in a graph, you can do it. So, okay.
I have a question. So one of the stated objective of NNEF is interportability between TensorFlow, Caffe, and some other framework. So the main difference between TensorFlow and Caffe when we talk about interportability is the level of operation. So TensorFlow gives you primitives to do the operation at very low level, and the combinations in which you can create these operations becomes tremendous, a lot of things, right? But Caffe works at a very high level, layers and things like that. When you talk about interportability, providing some utilities like to do the conversion and things like that, you had to basically construct, like you had to take the low level primitives and abstract it into high level layers and things like that. So is the current implementation is capable of, I mean, it's not part of standard, I know. It's a part of utilities, what you are providing. Is it capable of doing those kind of abstraction from the graph, or is it one-to-one conversion? How, what is your strategy when you claim interportability, basically?
Okay, let me talk from Khronos perspective, because I don't want to get into the particular discussion here, right? So, what NNEF does is, whatever you have in Caffe, at that level, NNEF, you can represent that. If you have TensorFlow, you can represent that using low-level primitives. Converting from, let's say you want to take a Caffe, convert it to NNEF, and from NNEF you want to go to TensorFlow, probably that's easy. That's not your question. You want to go from TensorFlow low-level, go back to Caffe.
Yes.
So it's going to be very similar process in kind of looking at OpenVX in general. You have defined multiple operations. How do you fuse them, right? And that every vendor tries to implement it on their hardware. If somebody has a really strong use case that they have to convert, go from TensorFlow, these low-level primitives, to go to Caffe, they have to implement a way of exporting from NNEF into the Caffe, right? Who's going to do that is pretty much whoever needs it. As far as standard goes, we gave a mechanism to be able to represent whatever an input comes from. If it comes from Caffe, we can represent it. If it comes from TensorFlow, we can represent it. Always the goal is, if I import from TensorFlow, I should be able to go back to TensorFlow. If I import from Caffe, I should be able to go back to Caffe. And if the operations are portable across these two, we should be able to map it across these two. I'll take one example. Let's say you have, I don't know if I'm kind of getting biased on this. Let's say you have a Onyx representation you want to move to TensorFlow, or you have a TensorFlow that you want to move to Onyx. You want to use NNEF in the middle. The trick is going to be certain things cannot be represented. There's a certain operations that are kind of exclusive between these two. There's no way to translate them. So what NNEF gives you is a mechanism through which you can represent it, right? A consumption is up to the consumer side. Now, if I can't represent matrix multiply in one of these, there's nothing I can do other than I have to go each element, and I have to kind of boil down to go into the low level if it's feasible. Maybe it's not that useful.
I understand the difficulty in doing that, but my concern is that defeat the purpose of the standard. Basically, you become a superset. You provide so many operators to take care of all different platforms. Now, instead of course, the naming convention, other things will be same for all the primitives and things like that. But it's just, we have not solved the primary problem of having different frameworks, right? So because each framework gives their own primitives and things like that. So, I mean, format is the least concern for me, like this thing, right? I mean, I can parse, I can write one more parser. That's not a major concern. A major concern is the operator interportability, right? So this framework provides operation at this level, and so that problem still will continue to exist even after NNEF standardizes all this thing. That's my concern.
Yeah, I think there are two different problems, and syntax, don't underestimate that. That's a huge problem. That's the reason we have the NNEF to start with. And surely this other one you're bringing up is a challenge. Now question comes down to maybe there's a third party who has an IP and who knows how to do it, and they can do this conversion smartly, and they can kind of create a product by themselves. Maybe I should leave that to Neil or Peter or Frank to give a take on that. You guys have any feedback? I think it goes back to GLTF, standard things. If somebody has a custom format, if you can't represent it, if you're kind of using GLTF as an intermediate to get input and get output, how do we deal with that?
Thank you.
Yeah. NNEF does have sort of low-level primitives, though, so the idea is closer to TensorFlow in that way. So going from the other things to NNEF is pretty straightforward. Is going the other way where as you said, if you express something that's not a cafe layer, that's harder. And it's something we'll welcome your help on. All right, so thanks, Radha, and it's good to see the code, see this stuff is real. We'll go back to slides here for a little bit. I'll talk about the safety critical version of the spec. It's based on version 1.1 of the spec, and what we did is we took the spec as we had it and looked at, well, what are the requirements in a safety critical environment? And so there's sort of standards out there for developing safety critical products, and it's not just did you test your product, but really there's a whole process of you need to follow this process in order to claim that you're safety critical. So it's not just your result, but the process you went through to get it. And so what we've done with the safety critical version of the spec for OpenVX is we put in the hooks in there to make it so that you can follow this process, make it easier for you to follow this process. And so we don't, by just looking at the spec and saying you conform to the spec, that's not necessarily guaranteeing that you've done it safely, but it does help you to follow the process. And so there are things like ISO 26262, which has a process that you should follow in order to create your product, and you use this V model where you start with the requirements, so you get an increasing level of detail. You start with the requirements at the high level, you go to the next level of detailed architecture design, then you do the implementation, and then you have, after you get that low level implementation, you back up, you have unit tests, you have system tests, and you have your system requirements. And so what you need to do is, or what we need to do in terms of the spec is to provide the hooks or the annotations in the spec that enable you to do this. And so what we've done is we've added in this safety critical version of the spec these tags for everything that we consider to be a requirement. If you're going to follow the OpenVX standard, you need to, if you look through the text, it says something. This shall do that. This will be the result, blah, blah, blah. All of these are now tagged so that you can actually trace them as you go through this V model of development, starting from the requirements. Each requirement is tagged, and you can make sure that those are implemented in your architectural design, and then the code, and then you have a test, and you go all the way back up, and you can see that as you've gone through this entire process, you have validated that this requirement has been met in your system. So it provides that traceability. And you can see the example here, create remap, the fact that it creates a remap object, that's a requirement. And then on each of the parameters for that, it says exactly what that parameter is, and that requirement is tagged so that you can then have a test that says, in fact, is the height of the image what's being passed here, and that sort of thing. A few other things that we did, actually modified the header files. So if you go to the OpenVX webpage, you become an adopter. There's, in addition to the spec there's a set of headers that you can use in your implementation. And we changed those in order to be MISRA-C compliant. So we got out, I don't remember which one it was. There are MISRA-C checkers out there. So you run your code through it, and it flags stuff. And some of the things that it flagged for us here, actually the way we were doing enums was well, it was flagged, and so we changed it so that it would be using pound defines everywhere in a straightforward way that was MISRA compliant. There was also a particular object, or a union actually, that was being used in a way that MISRA doesn't like, so we made a small change there. And then there's a few APIs that were passing pointers, and in general you want to pass the size of the pointer as well as the size of the thing that is being pointed to as well as the pointer, so that you can make sure that you don't run off the end of the memory area and implement the APIs in a safe way. So we changed a few of the APIs to actually pass the size as well as the pointer. So that's sort of the spec differences and sort of some details, but then I guess really the major difference in the way that you use this spec, this safety critical spec, is that all of the features in the spec are divided into what we call the deployment feature set versus the development feature set. So the development feature set is, you're in the lab or you're developing your product and you call all these APIs and you create graphs and you change that around until you get it how you like it. When you get it how you like it, and there's this verify step that you would say, oh, I'm going to verify the graph to make sure that it's correct, and also I'll map it, compile it to my particular target, all of that stuff. You can do all of that, and you iterate that on the deployment side. Once you've got it how you like it, you verify it one time, and you store it in a binary format, so that when you actually run in the deployment environment, say a car, you're not going to compile the graph. You're not going to create the new graph and move things around. You're just going to load the graph that's already been compiled, already been mapped to your hardware. You load it and you run it. And so all of the features in the OpenVX safety critical spec have been divided, segregated into these two parts. So this is just what I just said. You create the OpenVX graph, and you verify it, and then you export all you export the graph into this binary format, and then you release them. That's what you do on the deployment, or excuse me, the development side. On the deployment side, all you do is you create your OpenVX context, you import this object from the binary, and then you can run your graph. And then, of course, when you're done, you release all the objects. So this is the division into these two different parts. So for the deployment, really all you need is to be able to import graphs. You can create a context, you import a graph into it, you provide data objects for the input to the graph, and then you can process the graph. You call the function process graph, and that would be of the graph that you loaded from binary. And then you need to look at the outputs and the results that you got from that. And that's it. And all the other stuff down below of where you construct the graph and you create individual nodes and you verify the graph, that's all done on the development side and not during deployment. There's a few other things that are not supported in the deployment side. There's a facility for all of the OpenVX functions where you can call them directly without creating a graph. That's not supported here. You got to create a graph so that you can export and import. And there's some logging and performance features that you would do sort of in the development phase, but then not in deployment. And the graph export, again, on the development side, you can export, but on the deployment side, you just import it and run it. So it just sort of graph of how this thing evolved. Of course, we had 1.0 and 1.1. The 1.2 spec with some additional nodes was actually developed in parallel with the SE spec. And so the SE spec is based on 1.1, has the functionality of 1.1 with those SC specific changes that I just mentioned. And when we go to 1.3, which is in development now, and we're targeting early next year for release of that, then these things will be merged. And there'll be one spec, and it will have a safety critical option that you can say, okay, if I'm doing the safety critical stuff, I'm conforming to the rules. So, summary, we've got this annotated spec with all those tags and those other changes that we made for minor things to the API so we can make it MISRA-C compliant and safer. And we divide it into these two feature sets, deployment and development and deployment. There's also this import-export. In the standard, say, the 1.1 spec and the 1.2 spec, this idea of exporting a graph as a binary and importing it in, again, that's an extension. But if you're going to use the SC, it's sort of built around this, the fact that there's two different kinds of feature sets. So it's a requirement. That import-export extension for SC is a required feature if you're going to use the SC spec. Whereas in the 1.1 and 1.2 specs, it's an option. It's an extension that you don't have to necessarily support. And as I showed in the previous picture, when we get back together on 1.3 version of the spec, that import-export extension, it will be a requirement in order to be compliant to version 1.3. And so instead of having two separate specs, when we get to 1.3, we'll just be having one, which you can either be safety critical or not based on your requirements. That's it. Any questions?
What is the rationale for how to define those enums? Did they explain that?
Yeah. So there are ultimately the MISRA-C complained at us, and it was the easiest way for us to fix. There are I believe you can use enums within MISRA-C, but there's limitations and stuff. And the way that we used enums in the code, it's pretty strange. We've got sort of chains of enums and things where things are defined in terms of other. Anyway, it didn't like that, and this just made it simpler for everybody.
It's the casting that it didn't like. Explicit casting of enums it didn't like. We went through this part. Why have an extension? I guess a couple of things is basically we can make the features available quickly for a feedback from the community. At the same time, we don't have to wait too long for getting into the main spec. And some of them we're going to keep extensions separately because it may not even belong in the core spec because only few vendors are interested in it. Right? So there are a lot of extensions in the OpenVX, and you see kind of the different OpenVX versions that they're supported in. And now I'll be just focusing on, actually I'll just go over three. I think most importantly the pipeline and import. Those are kind of new ones and they're a little tricky. So I'm going to skip neural network because we have went through enough about that detail. So import, export, extension. Frank went through really detail in OpenVX SC. This is already absorbed, most of it, so we don't have to go over that. So kernel import. So this is an extension that we got it just approved. We just released this week. Which week? Last week, yeah. So what this allows is provide a way of importing, let's say, a subgraph that you pre-compiled. That subgraph could be a neural network or could be a very custom code that you build. Let's say one way I can think of it is, let's say I have a very complex code. I want to compile that into some kind of a SPIR-V, and I have in my runtime, I have a means to take a SPIR-V and compile it during the last stage and create that program at the end, being able to instantiate as part of graph. I could do that. So what we did is, instead of trying to standardize what format the import is, we said, okay, we need a common API because that's what everybody will be using. The binary, the program that comes in is very vendor specific, especially if you take something like a neural network. And let's say I have a network coming in NNEF format. And let's say if I'm a GPU, I would want that to be pre-compiled in a certain way. And my binaries are going to be different because I don't want at runtime to be able to compile that. If it's a DSP, they're going to do it completely differently. If it's a SOC with fixed function DSP GPUs, they might want to build it completely differently. So what this API gives you is to be able to import a binary in a vendor-specific format. Once you have a kernel object there, now you can instantiate that kernel as a node. You can instantiate multiple nodes with that particular binary that's going in there. And best use case, actually, we started this one with NNEF in mind, and we're trying to figure out how to do it. This is the best we could come up with. And the next part we're looking at is, could we ingest NNEF as a standard format? That's still ongoing discussion. We'd love to get some feedback from the industry. Let's see. Pipelining extension. This is one of my favorite extensions. The hard problem today is when you describe a graph, and when you have a hardware that has multiple blocks, CPU, GPU, or in certain SoCs you have some DSPs, some ISPs, some fixed function hardware, and it is not easy to just say run the whole graph at once. And let's take a diagram here. We just picked an SoC here. And let's say if I have a graph that has a sequence of 3 nodes. If all you're doing is just say process a graph, that means you just ask, give an input, wait till the output is ready. And if I have 3 different devices, I know node 1, node 0 is optimal running on ISP, different node is optimal running on different hardware blocks. If you try to look at the pipeline, with that pipeline, you kind of see a lot of hardware is not utilized. You're not making use of all the hardware, and so your throughput is going to be low. So what pipeline lets you do is allow multiple, you should be able to give multiple initiation of the graph. That means you should be able to schedule multiple inputs simultaneously, so that underlying implementation should be able to schedule that in a pipeline, or whether it's a batch format, right? And a batch is really good for things like GPUs. And if you take SoCs like DSP and ISP, there pipeline is really good. So what we did is to be able to come up with a means that a developer express their intent in terms of how much latency can they tolerate, how many input sets that they want to submit, at what frequency they want to submit. They can express that intent using the API. And underneath implementation now looks at what is your developer intent and tries to figure out a way to map it to all this pipelining or batching. Those scenarios. You can see simple example here with the pipeline. Let's say in this particular case, I'm just queuing up a frame, every frame, let's say 10 milliseconds in this particular case. Then you can see the latency is going to be 30 milliseconds, but my throughput is going to be like 10 milliseconds per frame coming through. So this was very hard to come up with, because in working group member, we have diversity of people with different kind of hardware. And coming up with something looking from a developer perspective and having an ability for each vendor to map it down to their hardware is a very hard problem. We had several proposals coming from several members. We tried to cherry pick what's the best way. And finally we settled. I'm glad we could settle on this one. Now, other one is OpenCL, OpenVX interop. I think we briefly went through. So today, without this extension, an application wants to use OpenCL. Along with OpenCL, they have to kind of take these buffers, move it to the host, copy back and forth, which is going to cause a lot of overheads. So what we did is this extension, we provided a mechanism to be able to exchange buffers between OpenVX and runtime, OpenCL runtime, or the application, and provide a command queue so that both the OpenVX framework as well as an application, or even some custom nodes, custom kernels that an application wants to create, or third-party vendors to create. What this does is it lets you get async operation between the runtimes and the applications. So there are no overheads for data transfer. In most of the cases, data transfers are the killers. Getting the key performance out there. What else? Yeah, I think we talked about data, and how do we accomplish is by sharing a common OpenCL context command queues and being able to exchange buffers asynchronously. And you could basically, when you do a map, earlier you see, you heard about the map and unmap calls, which were kind of giving you host pointers. Now you can explicitly say, I'm interested in OpenCL buffer. So if underlying implementation figure out a way to get you OpenCL buffer, it's especially advantage if underlying implementation already using OpenCL buffer, then it doesn't have to copy data back and forth. There are other extensions, but I think in the interest of time, I'm going to skip it because we're already close to 12:30. So I would like to pause here and take some questions.
You mentioned annotation is done in the generated OpenVX code. So when I want to annotate which node is done, how this is, can you elaborate a little bit how practically, what's the flow for that?
So the API is high level, broad enough where the developer doesn't have to specify where to put node 0 on which hardware to put node 0 on node 1 on node 2 on. All you're specifying is I want this functionality, and you're going to be able to say I can tolerate up to, I can queue up to 4 frames, right, or 3 frames. You can basically you specify that, and underneath hardware vendor, basically hardware implementation looks at it saying, okay, user want to queue up 3 images one after the other with this kind of latency, and they figure out, and implementation figures out depending on what hardware they have where to schedule it.
So the annotation of the queuing is done still at the C level?
Yes.
Okay.
Well, the queuing, yeah. All you do is, the API we give is to say simply enqueue this data, means start schedule at the top level. You just want to say, let's say if I have a batch of 16 images, I can simply say, okay, schedule all these 16 images at once. Where the graph specifies only a graph, let's say if the graph specified taking an image and getting output as an image. Now we can give a set of 16 images and say run all of them through. That's like a batch mode. Or you can say, you can keep saying, okay, schedule image 1, schedule image 2, schedule image 3 at a fixed interval, like every 10 milliseconds. And you can say, wait till the third one that I scheduled before. So that way there's kind of latency before, and the underlying hardware can just queue things up.
Is there an example or guide for this kind of thing?
Unfortunately, I don't have it here, but I think if you look at the extension specification, there are examples. Okay. We did put some examples because this is a very hot topic.
Okay, thanks.
To understand, yeah.